economic growth and industrial development bring air quality problems, and knowing how to deal with it in the future is vital for us to keep progressing as a society. Now we have better tools, better technology, and more knowledge. We can act faster and more efficiently to address pollution issues.
Course AQ is an international cooperative field campaign between NASA and the Korean National Institute for Environmental Research.
Ministry of Environment of Korea has put in a great deal of effort into improving air quality.
By working with our Korean colleagues, we've been able to design a campaign that is very specific to their knowledge of the air quality problem for the past decades.
The venture with NASA has provided us with many research opportunities.
The air in our planet does not know national borders or countries. A worldwide effort is needed so that what we do in the name of progress does not have a negative impact on our health and helps preserve the only home we know, Earth.
Course AQ combines satellite-type observations with ground observations and airborne observations to create the most complete picture of air quality we've ever created.
Explore with us. Take a deep breath and join us on an expedition that will investigate a major public health problem, air pollution.
One of the difficulties in understanding air quality is that pollution that affects your health the most is not the initial component put into the atmosphere.
Under certain atmospheric conditions, some of these pollutants react with each other and produce new harmful agents like ozone.
There's three key ingredients to make ozone: NOx, hydrocarbons, and sunlight.
So think of ozone as an important cleansing agent from the atmosphere. When you have a big stain to clean, you use a lot of cleanser. And when you create a lot of pollution, a lot of ozone becomes evident in the atmosphere. That's helping to clean the atmosphere, but it's also impacting our health. We have primary pollutants. Nitrogen oxides and reactive hydrocarbons are most important in the formation of ozone.
Your car emits both NOx and hydrocarbons, sort of unburned fuel.
But the ozone itself comes from the chemistry, so we call it a secondary pollutant because it results from the chemistry that occurs after the emission of the nitrogen oxides and the reactive hydrocarbons.
When nitrogen oxides and hydrocarbons react with sunlight, they produce a harmful secondary pollutant, ozone. But wait, isn't ozone good for us? Well, it depends.
The role of ozone in the atmosphere is quite complex. In the stratosphere, ozone is a great benefit because it protects us from UV radiation. In the lower atmosphere, ozone is also a benefit because it's responsible for initiating the chemistry that cleanses the pollution out. But when pollution levels are very high, the chemistry runs amok and you create very high levels of ozone. And those ozone levels can become so high that they become reactive with our own body tissues and become a problem in terms of health.
Photochemical smog is considered to be a problem of modern industrialization. It is present in all modern cities, but it is more common in cities with sunny, warm, dry climates and a large number of motor vehicles. It can also affect rural areas, where agriculture, trees, and forest fires can release a considerable amount of volatile organic compounds, or VOCs.
What are the sources of VOCs? Well, we have just the evaporation of gasoline when you're filling your tank, petrochemical plants, the refineries that are making gasoline for us from oil, and also the plastic companies that are making plastics, polyethylene, polypropylene.
In terms of reactive nitrogen, man's activity far outpaces the natural sources, and so we can say that when nitrogen oxides are present, that's man. When you talk about reactive hydrocarbons, actually vegetation plays a major global role in creating them.
Trees can emit that pine tree smell you smell, but also a lot of the deciduous trees are emitting isoprene. Isoprene is very reactive and very good at making both particles and ozone.
But fortunately, they create very specific molecules, and when man creates pollution, it creates a different chemical mix. And so we can look at the constituents of the reactive hydrocarbons to determine whether it's nature or whether it's man.
But because these compounds travel with the wind, they can affect different parts of the world. Recently, scientists from other airborne campaigns were able to trace the origin of unusual high levels of ozone in the air above the western Pacific Ocean. They found that they were linked to the organic compounds released by forest fires in Southeast Asia and Africa, half a world away.
The atmosphere is a shared resource, and we're seeing more and more that the entire northern hemisphere is suffering from pollution background levels that are due to all of us, not just one.
Everyone living in a big city around the world is breathing polluted air, and it is having an impact.
It's part of the tug of war between progress and the price that we pay for that progress. And so that balance needs to be maintained into the future as we continue to develop economically, develop technologically. We have to pay attention to how that's impacting the air quality.
Our world is an interconnected system, and the impact of air pollution goes beyond the air we breathe.
All of the processes that are emitting and causing air pollution are also putting CO2 into the atmosphere, causing climate change, global warming.
It also affects our soils, our glaciers, our oceans, our climate.
And this is a problem that's going to affect our children and our grandchildren. So it's very selfish of us to ignore this long-term problem that is created by us.
In a laboratory setting, you can artificially control different parts of the problem, so each effect can be isolated. That's hard to find in nature.
Seoul, South Korea. A megacity with over 25 million people and a population density which is almost twice that of New York and 8 times greater than Rome. Despite being a modern and massive megacity, South Korea still counts with many forest and rural farming communities throughout the country. But why is South Korea an ideal natural laboratory to carry out air quality studies?
We have a bunch of factors. We have a very large city, a mega city, the 4th largest city on the planet, with lots of cars, lots of power plants. And then downwind from that, we have a forest. So we have the urban plume reacting with the natural emissions from the forest.
This is a perfect place on the globe to try to understand how the mixture between man's emissions and nature's emissions can create poor air quality.
Air pollution is an important environmental problem in modern societies. The rapid growth of new economies and industries in developing countries makes it very difficult to address environmental issues.
Korea has been developed very quickly after the Korean War. Actually, economic success gave us lots of benefits to the people. However, this also brought many environmental issues, including air quality.
So general public has been known about the yellow dust issue before, and in recent they start to learn about the fine particle issues and ozone issues. They're starting to pay their attention to those newer issues emerging to our society.
Korean government has been making persistent effort to improving air quality. We participate in this project as though understanding of current situation with aerial, ground, ship, on the top of current simple ground observation, crucial in future improving air quality.
We are definitely pay attention to solve this issue, and general public wants to know how we can actually achieve that goal.
Developing effective strategies to balance the economic growth and the good health of the population is key to continue growing and prospering as a society.
Unfortunately, policy always lags emissions, and so it usually takes time to understand what's causing the poor air quality, and then regulations can take effect.
It's a tough problem. We haven't solved it completely in the U.S. But here, I think you're right. We're learning a lot more about the specific sources in this area so that here locally the government can decide what's the most effective strategies to use, because we don't want to hinder economic development. We just want to know what are the smartest choices you can make so you get the best bang for the buck.
In the United States and in Europe, this has taken place over a long period of time. Things in Asia are growing very rapidly, and so we're in the middle of that process.
But the difference is that now, with our knowledge and technology, we are better prepared to address these complex environmental issues.
In these days, many countries in East Asia have been developing very quickly as well. Course AQ mission makes people aware of the seriousness of current air pollution.
So we are thinking, based on this mission, more general understanding, getting better and better, and eventually we can find something to actually reflect to the strategy.
Chorus AQ mission results will help develop improved ways to assess this challenging task.
Current investigation will definitely help us gain deep understanding of air pollution phenomenon in global scale.
This is a lab, measuring instrumentation, probes, sensors, gas and liquid chemicals, computers. Yeah, this is a lab, but maybe not the lab you would expect. Meet the NASA DC-8 Airborne Laboratory.
The airplane is designed for different instrumentation suites depending on the missions that we fly. So we have multiple zenith ports that look up, we have multiple nadir ports that look down, and of course many of the window blanks there.
There are 25 instruments on board the aircraft, not only from NASA but from many universities and other government labs and organizations, and together they paint a picture of the atmosphere that can allow us to completely evaluate what emission sources in the peninsula are contributing to poor air quality and how the chemistry actually works in terms of the outcome at the end of the day when ozone and particles are such a concern.
Yeah, this integration is about as big as we do, and if you've seen on board the airplane, you can see it's very full with all the racks and most of the windows, covered with the in situ probes that are there.
The Chorus AQ campaign will gather air quality data in and around the Korean Peninsula from multiple sources, such as ground stations and maritime sensors. However, the Chorus AQ aircraft will be the ones to provide the most detailed information over a larger geographical area and at different altitudes.
So in order to understand how it all works, we have several aircraft that we have to fly. One is the one I'm standing on right now, the NASA DC-8. The DC-8's role is to measure the atmosphere directly. From this aircraft, we can measure literally over 100 different compounds in the atmosphere.
The airplane flies as easily at 500 feet as it does at higher altitudes. That enables us to do both remote sensing, which is using radars or lidars, as well as we can fly lower, we can do vertical profiles with our in situ sensors, which is currently what we got mostly on this airplane.
In order to understand the atmosphere, there are many different molecules that we have to measure. The satellite will not see all of them. And so by being able to measure what the satellite will see, and at the same time see all of the details, we can begin to understand what sources and what meteorologies and what combinations of conditions will affect what we see from space.
By combining detailed measurements from aircraft with those made by satellites, we can get a better picture of pollutants in our atmosphere.
So this aircraft carries instruments that work just like the satellite instruments. The higher we fly, the wider the patch of Earth we can see.
During the campaign, NASA King Air aircraft will mimic the measurements future satellites will make.
We fly at about 28,000 feet, and at that altitude we see about a 5-mile wide patch of ground. Like mowing the grass, we're just trying to cover a patch on the ground continuously and make a map of what the pollutant distribution looks like.
So we have a small King Air aircraft flying above all throughout the day, measuring the way the future satellite will measure air quality. Meanwhile, the DC-8 flies underneath, showing what the distribution of pollution is above the ground. That allows us to understand how to connect what the satellite sees with what's at ground level.
Chorus AQ has in its team 2 smaller aircraft equipped with atmospheric chemistry measuring instrumentation. A King Air from NASA Langley Research Center, and a King Air provided to the Korean National Institute for Environmental Research by Hanseo University.
The Hanseo King Air aircraft is relatively smaller than DC-8 in NASA. It can freely access source of pollution and measure air quality capital territory that cannot approach using DC-8.
Working all together, scientists from the Chorus AQ campaign will provide valuable data and test the technologies needed to better understand air quality and the flow of pollutants within our atmosphere.
We can only fly the planes for a very short period, but the details that you get from the aircraft help inform the observations from space and from the ground, and how models can interpret those observations.
From this mission, we'll have better models and better mission data for Asia, and so we'll be able to extend the usefulness of this well beyond South Korea to other developing cities around the world.
We have the tools to study our atmosphere. Now, let's go exploring.
There's one thing that stands between us and the harsh environment of space, our atmosphere, the part of Earth that sustains all life. But here, in the closest town to the North Pole, it's slowly leaking away. A team headed there to launch rockets into the leak, but it's not the lack of atmosphere that they're concerned about. The leak is a natural process that will take billions of years, so we're not going to run out anytime soon. It's part of the larger story of how a planet's atmosphere changes over time, a key factor in the search for life on other planets.
We have 35 residents and 60 of our team together in a town that is completely isolated. There's a plane twice a week, and there's 1,000 polar bears nearby.
This is Doug Rowland, a NASA scientist who's taken his team to Ny-Ålesund on the island of Svalbard. The island lies beneath one of 2 regions near Earth's poles called the cusps. It's where we can access space directly, and where 100 tons of atmosphere escapes into space each day. This escape gives clues to how long an atmosphere will last, and ultimately, whether it stays around long enough to sustain life.
What we're trying to understand is, how did Earth's atmosphere evolve over time? And how do other planets that might be like Earth or more dissimilar to Earth, how did their atmospheres evolve?
So Doug joined forces with Göran Moen, a professor at the University of Oslo, who started the Grand Challenge Initiative, CUSP. It's an international mission to launch 12 rockets into the Earth's northern cusp. And Doug, he's the mission leader for the first 2 rockets of the campaign.
We don't want to waste our rocket. So it took us 3 years to make the rocket and only 15 minutes to use it, and I don't want to waste my shot here.
He's using a sounding rocket, which is different from the bigger rockets that carry satellites and humans into space. It's a small suborbital rocket that flies briefly into space, collects real-time data for around 15 minutes, then falls back to Earth. It's affordable, quick to build, and can launch towards a precise point.
The major advantage is that you can launch into a target on the sky.
But there's a limited launch window and only one chance to get the launch right.
We have these unguided rockets. They go where you point them, unless the wind is blowing, because the wind literally just blows them over. We don't launch when there's high wind.
So to measure the winds, they launch balloons with GPS trackers. They're released every 15 to 30 minutes, and then they're monitored to see how fast the winds are carrying them.
The ground winds were 12, 13 meters per second, gusting 17, which is way off.
You're filled with trepidation. Oh my gosh, this thing that I built, is it going to work after all this? So I think we're going to scrub for today. I'd like to thank everyone. I think it was a great performance. Thanks a lot.
This means that we are scrubbing this operation for today and we'll try again tomorrow.
The mission is named Visualizing Ion Outflow via Neutral Atom Sensing 2, or VISIONS 2. In short, they're looking at how oxygen is getting enough energy to escape.
It's a good test of how atmospheric escape works. Earth's gravity should hold onto the oxygen, and yet we see this gas shooting off into space. We're trying to figure out how that works.
That is a science question that has been hanging around for 4 decades.
Fortunately, anyone can see atmospheric escape at the right place and time.
In Svalbard, we have the so-called polar night. It's dark all 24 hours.
This continual darkness is key for witnessing this. This is the cusp aurora. It's a type of northern lights that appears between 8 a.m. and noon, and you can only see it when it's dark during the day. It looks similar to the aurora that occurs at night, but when these iridescent colors dance at this hour each day, 100 tons of oxygen escapes from Earth's atmosphere into space.
This is our sport now to chase the aurora.
Working with them is the iSCAT radar and Kjell Henriksen Observatory. They have additional instruments to find the aurora.
Sometimes it's cloudy, so we use radars to track the cusp. We can give advice that this is the right type of aurora.
This is the Wall of Science, a collection of data from satellites and ground instruments that helps them predict where the cusp aurora will be.
So the cusp actually isn't a fixed point in space, it kind of moves around.
What's controlling the cusp's movement is the sun interacting with Earth. Our planet is surrounded by a magnetic field that helps us hold on to our atmosphere. But at the North and South poles, the magnetic field bends inwards, creating a corridor between Earth and space.
When energy is released from the sun via a solar flare or coronal mass ejection, all of that energy in the form of radiation rides down the magnetic field lines of the Earth and is transferred and dumped into the Earth's atmosphere.
Electrons cascade into Earth's atmosphere. They accelerate and collide with oxygen particles, giving them energy to release light and sometimes enough energy to escape. Collectively, this forms the cusp aurora and streams of escaping oxygen.
This cusp is in constant motion.
And we've got a fixed trajectory. We really can't aim at where the cusp is. We have to wait for the cusp to come across our line of sight. Can you guys hear Chelmar? We'd like you, as soon as you see an indication the cusp is moving close, to move it, the radar dish if we can.
This is iSCAT. It's been very quiet, very difficult to launch.
Do you think we're going to launch today?
No.
Probably about a 60% chance of launching.
When we started seeing this really good data, this clock started counting down, and that's when everyone realized this is going to happen. We're going to launch.
We're doing everything we can to get that launch off before the aurora goes away. It is really, really challenging and nerve-wracking at that point. You can see the tension just rise in everybody when that happens.
And so everyone's watching their instruments, getting really excited, and then at T-minus 1 minute, all of us ran out to go see the launch happen. then we immediately turned around and ran right back in to look at all the data that was coming back from the instruments. You know how much time and effort went into it because we all worked on it, and there's just nothing that compares to that feeling.
Everybody in every one of those little places, really just so happy to contribute to getting this science. It's really an incredible experience.
This is a story about what it takes to launch science instruments into space, but the real adventure will be in the data they sent back. Hidden within the numbers will be answers that reach far beyond Earth, shedding light on how atmospheres throughout the universe change, evolve, and perhaps support life.
The Rescue Coordination Center started receiving distress signals.
The bridge was starting to fill up with water. The ship was sinking and got them out on top of the rescue boat.
Winds up to 60, 70 knots.
We started to separate one by one.
Wave height 50 to 60 feet.
Finally I was alone and no rescue boat or nothing. The rescue boat drifted away.
It's freezing out there.
All I had to do was just wait and hope some kind of miracle would happen.
There is almost no chance to survive in conditions like that.
AIS, the automatic identification system. All ships out on the open oceans are obliged to transmit their position and their identity and their direction of speed, heading and speed, etc. It's kind of like air traffic control for the sea.
It's very useful to help provide assistance to ships in distress.
First of all, to see, do we have assets in the area that could help somebody in distress. In the days before AIS, we didn't even know if there were any vessels in a particular area where we have an incident.
They were more or less invisible to the coastal traffic administration.
But as of today, if we have an incident out in open water, we have the chance to see what vessels are in the area and could contact them directly to route them to the position or the distress, and in that way, in a more effective way, rescue more people within a shorter time frame than we ever have before.
AIS receiving stations along the coast, they can only look a certain distance out into the sea.
Ships that go out beyond 75 kilometers outside the coast were over the horizon and invisible to us. But if you think about these signals going straight, they go maybe several hundred kilometers out into space. And you know what circles around the Earth about 400 kilometers above us? The International Space Station.
The European Space Agency contacted the Norwegian Defence Research Establishment and gave them the opportunity to mount an AIS receiver on board the space station to test out this technology from space. All our calculations indicated that this should work, but we really did not know before we switched on the receiver on the space station. 1st of June 2010, the system was turned on.
when the switch was flipped and the light came on and we were actually able to get the first data in, yes, the instrument works.
We all got very excited.
And suddenly we could see a whole world full of ship data. It was I would say, a quantum leap really in our ability to look at global ship traffic.
It's like a blind man starting to see.
Yeah, it was a huge relief and great satisfaction to see.
So this brought a whole new dimension to the monitoring of ship traffic on the open oceans.
Nobody knew how many ships really are out there at any given time, and suddenly we had, if not the complete picture, then almost a complete picture.
On a typical day, the space station is observing about 30,000 ships out on the open ocean.
I was kind of overwhelmed, I guess, by the response that's got. The space station really is an excellent lab for testing this type of technology.
This project demonstrates that the International Space Station is not just for science and astronauts, but it really benefits the whole mankind with down-to-earth applications.
Based on the AIS, we had another vessels in the area that we contacted who continued to the area, and they searched together with the helicopters. Nobody expected to find anybody surviving in that conditions. They actually spotted one man in the sea.
After floating in the North Atlantic Ocean for 4 hours, I was finally rescued.
Thanks to AIS data and AIS data from the space station, this lone survivor was rescued. A absolutely happy ending for him.
And luckily for technology that made something that was basically impossible to survive possible.
What happens if you wake up in the morning and you understand the state of the world as it is right now?
What could that data enable? How could people make smarter decisions? How could, for example, a farmer get better yield on his or her crops? How could somebody help disaster response? How can we use satellites to help humanity? That in many ways was the underlying thesis of doing Planet Labs, was to get data into the hands of people that could enable us to make smarter responses to that.
Planet Labs set out with the mission to photograph the entire Earth every day. And they thought, how are we going to do this? They said, let's build our own satellite.
Commercial imaging satellites, they're very large. They are very expensive. We took a different approach.
By making them really small, we can launch lots of them, and by launching lots of them, we can cover this, to get to this mission of imaging the whole Earth every day.
If we can do that, then we can literally change the way that we see the world.
And they called it the Dove. It's about the size of a loaf of bread.
Our doves are basically mainly a big camera with a telescope looking down to take pictures of the Earth. We initially developed the first Dove satellite in our garage. So we kept on iterating the Dove design, we made it better and better, and eventually we put our first one into space. We had no idea what the quality would be like.
I mean, we didn't know if it was going to work.
But we got an image down and it was so beautiful that we knew at that point we could make this technology work.
Wow, we can really do this, and we can achieve this mission, which is something that is really needed for us to understand global change.
So we had done a couple of demonstration satellites, but the next steps we wanted to do was to scale it up, to test the first fleets of satellites.
But what made that possible was actually access to space.
So here's the problem, that in order to take pictures of the entire Earth every day, you're going to need more than 1 or 2 satellites. You're going to need a whole lot of satellites, and you're going to need to be able to deploy them really fast. And really, there's only one obvious choice on how to deploy that, and that's the International Space Station.
There was no other platform in the world in order to get access to space of that fashion in that time period than the International Space Station.
NanoRacks is our key partner with NASA.
At NanoRacks, we understood Planet Lab's vision, and we knew that we could help. We worked together to figure out what was going to be the best way to get as many satellites as possible, and we basically developed a new platform. It goes out of the GEM airlock. It's picked up by a robotic arm, pointed out into space, and it fires these little satellites off of the space station.
They were able to secure 28 of our satellites to be launched from the International Space Station, and that was known as Flock 1, our first constellation.
This opened up the whole world to satellite developers, people that could put things into orbit fast.
We now deploy these on a regular basis from the International Space Station. And now today, we're able to operate the largest fleet of Earth imaging satellites in human history.
And none of that would have been possible without the International Space Station.
The International Space Station does enable young, small companies like ourselves to get going in space.
The ISS provides a lot of opportunities for commercial companies to test and find where the market in space is going to be.
And so what we're seeing today is a proliferation of new ideas and new concepts. It's almost like it's a renaissance of what's happening in space. Buckle up and strap down, because this is going to be a rocket for all of us in the global community to be part of.
The first pictures now coming in from Puerto Rico after taking a direct hit. Hurricane Maria slamming into the island. One official saying the island is destroyed.
Hours with winds and rain, and didn't stop.
Power lines are down. Streets are impassable. Many roads are flooded.
High winds uprooting trees, overturning cars, and turning buildings into piles of twisted metal.
It is something that will change Puerto Rico forever.
We had no water, no food, no gasoline, no communication at all.
Not knowing where my next meal will come from, it hasn't been easy.
After Hurricane Maria, everything was gray, all the plants were dead. Hurricane Maria took the color away from us.
I am sure that these children will not be the same. They will not be the same. They are still struggling and trying to recover from this.
My name is Joe Acaba. I'm a NASA astronaut of Puerto Rican descent. I was about a week into my mission on the International Space Station. Hurricane Maria was forming up, and from there, if you looked out the window, Maria took up a big chunk of what we could see. It was going to cover the entire island. After the hurricane, their power grid was pretty much taken out. You just couldn't see the island anymore. The hurricane, I think, had a huge impact on, the island as a whole, but especially the kids.
Joe Acaba was our hero, and we need something positive. The students need something positive.
We wanted to pull through, forget all that happened, and lift up our spirits and lift off the island.
So I knew I couldn't do much from up on the International Space Station, but I did want to connect with the students to show them that there is hope and that there are people out there that care about them.
NASA has the STEM station, which allows the students and teachers to talk to the astronaut in the space station.
It's making that connection so that maybe, they become more interested and we can inspire them more to study the STEM fields.
So we were able to establish and coordinate with NASA one of these video conferences. Thousands of students from different parts of the island watching the video conference with the space station, talking to Joe.
This is Joe aboard the International Space Station. I have you loud and clear.
How do you compare?
What is the most impressive?
How did Puerto Rico look after Hurricane allowed to visit? How often?
What is the minimum number of?
It was awesome because, as soon as it came up, you could hear people clapping, people were excited. So even though I couldn't see them, I could feel them, and that was pretty neat.
It was amazing. He called from the International Space Station to see how Puerto Rico was doing, and that means a lot for us, a lot.
In May of 2018, I was able to go back to the island, my first time since the hurricane. It was a great opportunity to get out and kind of come full circle with those students, to go and see them in person and, kind of reiterate how important they are, and just to give them a little bit more hope, because there's still a long way to go on the island.
He's a hero for us. Kids love him, and everybody loves him here. Joe Acaba is the role model that we need at this time.
I want to be like him. I want to go far, and I want to be an example for little kids when I'm older.
Not only is the International Space Station a great tool for scientific research and exploration, but for students from Puerto Rico in particular, I think that having that video conference with them, it did provide some hope. It did provide some inspiration. And so it's just one of the benefits that we get from the International Space Station.
To support International Space Station, we're constantly having to build new hardware to send to space, but as well, we need to make training hardware on the ground. So we ask ourselves, what if we got high school students to build us some training hardware and get them out of the textbook, get them some hands-on lessons to work with, and by doing that, we'll be inspiring the next generation of students. So that's when we decided to create Hunch. Hunch goes to the local high schools, partners with the high schools, and gives these students opportunities to design, build hardware that will fly in space or be used for training hardware on the ground. Students did the design and engineering, the CAD drafting, the 3D print prototyping, the machining, the procurement of the hardware. All this done by high school students to get this article to fly in space. From the quality perspective, the students have exceeded all of our expectations. The hardware we're getting in is top notch.
This program actually helps them focus into the engineering and the STEM fields.
I've been teaching for 23 years. I've never seen anything that even remotely compares to having the type of impact on students that Hunch has had. Absolutely phenomenal.
Working with the Hunch program, we fabricated training hardware for the ISS.
I created and designed interactive simulations.
We're making a Mexican paella and hopefully gets chosen to go to the International Space Station.
From the Hunch program, I've learned how to use AutoCAD.
We learned a lot of teamwork.
I've definitely gained some communication skills.
We're learning more about food science, technology, but everything basically doing this.
It gives them a confidence that I don't think they would have had to that level before this.
Maybe I would actually be able to be an engineer. So it was never something that I'd thought that much about. And then I was working on this stuff that went to space, and I couldn't think of anything more exciting. And I still can't.
It's a pretty cool thing to be able to tell other people or family when you go visit that I work with NASA programs.
I mean, I told everybody, like literally everybody.
We have an opportunity here for them that is unbelievable.
It's kind of like getting a master's at age 16.
They truly have moved on to a level they wouldn't have approached or wouldn't reach, I believe, without this program and without the International Space Station.
Before the Hunch program, I really was just a C student with no direction in my life. And since then, I've been on the Dean's List for the past 4 years and will be transferring to pursue mechanical engineering.
It really helped me find my passion for aerospace. The Hunch program gave me my career.
The impact on their lives has been amazing. They're more successful, they're more driven, they're more determined. They know they can achieve. And that's all, I think, through this program, through the Hunch program and interaction with the International Space Station.
Today's telescopes study the sky across the electromagnetic spectrum. Each part of the spectrum tells us different things about the universe, giving us more pieces of the cosmic jigsaw puzzle. The most powerful telescopes on the ground and in space have joined forces over the last decade in a unique observing campaign known as GOODS, which reaches across the spectrum and deep back into cosmic time.
Hello and welcome to this very special multicast. We'll be exploring a unique collaboration between some of the world's most powerful telescopes, both on the ground and in space. Now to do this, we've set up a similar collaboration between the ESOcast, the Hubblecast, the Spitzer Space Telescope's Hidden Universe, and the Chandra X-ray Observatory's Beautiful Universe.
I'm Megan Watsky for the Beautiful Universe from the Chandra X-ray Center.
And I'm Dr. Robert Hurt for the Hidden Universe from NASA Spitzer Science Center.
It's the combination of deep observations from many different telescopes that makes this project so important.
The longer a telescope spends looking at a target, the more sensitive the observations become, and the deeper we can look into space. But to get the full picture of what's happening in the universe, astronomers also need observations at a range of different wavelengths, requiring different telescopes. These are the key ideas behind the Great Observatory's Origins Deep Survey, or GOODS for short.
The GOODS project unites the world's most advanced observatories. These include ESO's Very Large Telescope, the NASA ESA Hubble Space Telescope, the Spitzer Space Telescope, the Chandra X-ray Observatory, and many more, each making extremely deep observations of the distant universe across the electromagnetic spectrum. By combining their powers and observing the same piece of sky, the GOODS observatories are giving us a unique view of the formation and evolution of galaxies across cosmic time, and mapping the history of the expansion of the universe.
Now this is not the first time that telescopes have been used to give us extremely deep views of the cosmos. For example, the Hubble Deep Field is a very deep image of a small region of sky in the northern constellation of Ursa Major. This revealed thousands of distant galaxies, despite the fact that the whole field is actually only a tiny speck of sky, about the size of a grain of sand held at arm's length.
Now, with GOODS, many different observatories have brought their powers to bear on two larger targets, one centered on the original Hubble Deep Field in the northern sky, and one centered on a different deep target, the Chandra Deep Field South in the southern sky. The main GOODS fields are each 30 times larger than the Hubble Deep Field, and additional observations cover an area the size of the full moon.
These areas of the sky were already some of the most extensively explored, and so the combination of the existing archival data with the many new dedicated observations gives us an unprecedented view of the history of galaxies.
At ESO's Very Large Telescope on Serra Paranal, the 8.2-meter diameter giants were used for a total of almost 100 nights of dedicated observations. The telescopes made images of the region both in near-infrared light and on the boundary between visible light and ultraviolet light. At these short wavelengths, only telescopes on exceptional sites, such as the VLT's Serra Paranal, have a chance to observe through the Earth's atmosphere.
The NASA ESA Hubble Space Telescope observed the GOODS regions at optical and near-infrared wavelengths in order to detect distant star-forming galaxies, among other things. Now Hubble spent a total of 5 days observing the fields, spread over 5 repeat visits. Each of these was separated from the previous one by about 45 days. Now by spreading out the observations like this, Hubble was able to watch out for new supernovae appearing over the months, providing key information for studying the expansion and acceleration of the universe due to the mysterious dark energy.
But it wasn't just Hubble making space-based observations for GOODS. NASA's Spitzer Space Telescope imaged the GOODS regions in near and mid-infrared light for 5 days at wavelengths up to 30 times longer than the Hubble observations. These longer wavelengths are important for revealing distant galaxies whose light may be obscured by cosmic dust or stretched by the expansion of the universe, making them invisible to Hubble. For these distant galaxies, the Spitzer images also tell astronomers about their age and their total mass of stars, complementary information to the data from Hubble. Now, let's move from the infrared to much shorter wavelengths.
Also in orbit, the Chandra X-ray Observatory had already observed the GOODS field in many long observations taken over the course of a year. The Chandra images are the deepest X-ray images ever taken and detected more than 200 X-ray sources believed to be supermassive black holes in the centers of young galaxies. The X-rays are produced by extremely hot interstellar gases falling into the black holes.
These multi-wavelength observations identified tens of thousands of galaxies. To get a full understanding of the history and development of galaxies over the vast stretch of the universe's history, we need to be able to pin down their distances more precisely, to fix them in cosmic time. As these galaxies are so far away, the light waves we see from them today started their journey up to about 13 billion years ago. And because the universe has been expanding since the Big Bang, back then the universe was less than 1/7 of its current size.
During the billions of years of the light's journey, its wavelength has been stretched as the fabric of space has expanded. This effect is known as redshift because, for example, light that was originally blue or ultraviolet in color is shifted to longer and redder wavelengths.
Back on the ground, astronomers used spectrographs on ESO's Very Large Telescope to capture the spectra of galaxies, spreading out their light like the colors of a rainbow. Now, the spectra allow astronomers to measure the redshifts of the galaxies and hence their distances. An extensive campaign produced redshifts for almost 3,000 galaxies in the GOODS fields. Now, with this knowledge, we can place the galaxies at their distances along a vast cone of space, stretching out from our own vantage point like a searchlight beam into the cosmos. We can take an amazing journey through kind of a tunnel towards the edge of the universe. In some places, the galaxies cluster together, forming structures which are up to tens of millions of light years in scale.
Thanks to GOODS and other surveys of the same region, these areas of the sky are uniquely well studied, with high-resolution, deep observations across a wide wavelength range. Plus, there's more to come. For example, the Atacama Pathfinder Experiment Telescope, or APEX, has spent a total of 300 hours, nearly 2 full weeks, imaging the region at sub-millimeter wavelengths from its high site on the 5,000-meter altitude plateau of Chajnantur in the Chilean Andes.
Observations at these wavelengths are ideal for finding the redshifted light of distant, dusty galaxies in the very early universe. Because of the longer wavelength of its sub-millimeter light, the apex image is not as sharp as the visible light and infrared images. However, thanks to the deep Spitzer images, as well as images made at radio wavelengths, we can match up and identify the objects found by apex with galaxies seen at other wavelengths. The sub-millimeter light glow reveals that hundreds of stars are being formed per year in these galaxies. In the next couple of years, ALMA, the Atacama Large Millimeter Sub-Millimeter Array, currently under construction on the same plateau as APEX, will begin its first science observations. Also observing at sub-millimeter wavelengths, it will have much greater sensitivity than APEX, and resolution even better than Hubble. ALMA will revolutionize our understanding of the early universe, by revealing many more distant, dust-obscured galaxies that cannot be seen at all by visible light and infrared telescopes.
These projects are an excellent example of how great observatories are joining together across the electromagnetic spectrum to give us a more complete view of galaxies over the history of the universe. Already, astronomers have written over 400 papers based on these data, with even more in the pipeline. And on top of that, the observations of the goods fields will continue in the future. These patches of the sky will be prime targets for the next generation of telescopes, both on the ground and in space. And astronomers around the world will use these data to learn new things about the universe for many years to come. Saying goodbye to our friends at the other observatories, this is Dr. J, signing off for the ESOcast and the Hubblecast.
This is Dr. Robert Hurt signing off for the Hidden Universe and the Spitzer Science Center, reminding you there's a hidden universe just waiting to be discovered.
And this is Megan Watsky, signing off for the Chandra X-ray Observatory and the beautiful universe.
Join me again next time for another cosmic adventure, which I'm sure will surprise us beyond our wildest imagination.
NASA researchers spend weeks, even months at a time, in remote locations around the world, collecting critical data about Earth's environment. Many studies are done from the air, using NASA's fleet of research aircraft. One such mission is Operation Icebridge, a multi-year study of polar ice conducted by the NASA Airborne Science Program. Icebridge sends NASA's P-3 flying laboratory to Greenland and Alaska in the spring to study changing ice conditions in the Arctic. A second aircraft, the NASA DC-8, flies from Punta Arenas in southern Chile in the fall to measure land and sea ice over Antarctica. It takes months of planning to execute a major international mission like Icebridge. Diplomatic clearances, configuring the aircraft with scientific instruments, and finding facilities that can support the people and the airplane itself are just some of the preparations needed for Icebridge to meet its mission requirements and goals.
To deploy to someplace like Chile, we plan a good 6 months before the mission to bring everything together so that once we arrive here, we're ready to execute missions on a daily basis.
Typically a mission director, a mission manager, program manager, we get called different names. We'll do the site surveys for the location, liaisoning with the government, of the host government to the host airport. That's the real legwork that's done prior, is coming out and making sure that they can house and feed us and take care of the people in the hotels. You name it. There's a lot of little tiny details that can't be overstated.
The biggest logistical challenge for the project as a whole is to set up all of the lab space and the facilities so that the scientists can process their data and make their decisions about which project.
Logistics is huge for something like this because we have to make sure we can all support the people in the field as well as the aircraft. So we think a lot about aircraft spares and then little details about the support equipment for the airplane.
Usually on every deployment we're going somewhere, there's at least a group that goes out and scopes it out. A lot of it's done like while we're working other missions. And they will talk with the airfield, set up and tell them what we're going to be doing. And then as they're communicating back with us with what capabilities the airfield has to support us, that way we know what to ship.
For a deployment more than 6,000 miles away in the southern hemisphere, the maintenance crew needs to carry an extensive payload to maintain the DC-8 on site and keep the mission on schedule.
Yeah, we put them right on the side there. Yeah,
More than 13,000 pounds of cargo are packed on the DC-8. Everything from spare tires, parts, and tools to basic comforts of home for the near daily 11-hour research flights over Antarctica.
On a deployment like this, we bring the equipment with us, and we also ship a lot of other things by sea in a big container so that we can keep the airplane moving. It'll come back from a mission. If there's anything wrong that needs to be repaired before the next flight, we have the maintenance crew to support it during the night and get it ready for a mission the following day.
The DC-8 flight operations team works around the clock to support Operation Icebridge, providing ground support for takeoffs and landings, operating the plane on research flights, and making sure sensitive science instruments stay powered up and heated overnight. The airfield is staffed 24 hours a day.
We have a makeup of about 28 people supporting the flight operations down here, and that consists of the pilots, flight engineers, navigators, mission directors, and then the maintenance crew that's split between mechanics and avionics technicians.
The maintenance team often works on tight deadlines to prepare the aircraft for its next deployment. Just 10 days after removing one set of science instruments from a previous mission, the DC-8 is reconfigured for Icebridge. In 3 weeks' time, the plane is transformed into a working science laboratory with a suite of radar and laser instruments and cameras installed throughout the cabin, cargo pit, and fuselage.
Yeah, the unique thing about the DC-8 is that it was modified to accept, at this point, we've got about 100 different instruments that have been integrated into this airframe. And so part of the modifications that were done early on was to make the airplane as versatile as possible. So if you were to look through the airframe, you'd see cutouts in both the bottom of the aircraft and the upper side of the aircraft. And a number of the windows were modified to carry structural loads of instruments being installed as well. So we can look in pretty much every direction there is outside this airplane as we're traveling through the sky.
Once the science instruments are installed, the flight operations team conducts a series of ground checks and instrument test flights over the California desert to make sure the DC-8 is mission ready.
Looks like maybe it's level now. Right, looks like it's a wings level and a rock course.
So the reason why we picked these sites over the desert in California is because they have these dry lake beds there, and they are a very flat area that's ideally suited for our purpose. So we can put a GPS receiver on a car and kind of drive around on these flat lake beds, measure them, and then a few days later fly over the same area with the DC-8 and take a measurement from the air, compare the two measurements, and use the data from the ground to calibrate and validate the airborne measurements.
While the aircraft is prepared for the trip to Chile, the science and flight operations teams are required to undergo specialized safety training, regardless of if they've flown on the DC-8 in the past.
Well, for the DC-8, everybody who flies has to go through basically a safety briefing. We go in a little bit more detail because we do more things on our airplanes than commercial airliners do. From our pilots, they go through survival training, water and land, and depending on where they're going, some of them have been through Arctic. All of our crew members, they all have to go to altitude chamber, water survival, land survival, and what we do here is we just build on that and then try and bring anybody else that hasn't had any formal training up to speed so they have at least a working knowledge of the kind of conditions that can happen if something was to go wrong with the aircraft.
Safety equipment tailored for Icebridge is also packed on the DC-8.
Overhead compartments, we've got 20-man life rafts. There's 4 of those on board the aircraft. We have 2 what we call global survival kits, which has different survival items inside of there. For this particular deployment, we also have anti-exposure suits, which if they were to go into the water, we have enough for everybody on board the aircraft for that.
Once the aircraft and passengers are cleared to fly, it's time to pack up for the long transit flight from Armstrong Flight Research Center in California to the southern tip of Chile. The exhausted team gets an opportunity to rest on the overnight journey to Santiago, where a second flight crew is on standby to complete the journey to Punta Arenas.
To get to this part of the globe, it's about 14 hours of flying. We had pre-deployed a crew to Santiago to join the flight at that point so that the crew that flew all night could then step out of the cockpit and rest. And that allows us to continue on that next day down to Punta Arenas, Chile, without having to stop overnight.
It's a cold and windy welcome at the Punta Arenas Airport, the mission base for Operation Icebridge. The scientists and flight crew will call this place home until the end of November.
We are setting up base stations here at the airport that record the GPS data for various instruments. We are talking to people in the weather office, at the tower, the air traffic controllers, and that typically takes about a day, getting everybody settled in here and preparing everything for the first science flight.
With 2 complete flight crews available, science flights are planned on consecutive days to collect as much data as possible over Antarctica.
On a typical Punta Arenas deployment, we have about 300 flight hours. And if we fly as much as we can, which we typically do, we kind of travel a distance in Antarctica that's equivalent to 3 or 4 times around the equator.
I think this is a glacier we're crossing.
Flight tracks are carefully designed by the Icebridge science team months in advance. Survey lines need to be precise, not only to make repeat measurements in exact locations, but also to ensure the plane keeps a safe distance from specially protected areas and animal habitats. A sophisticated guidance system on the DC-8 helps the flight crew keep the plane on track and navigate around more than 1,700 known wildlife locations on the Antarctic continent.
Some of the flights are hand-flown using moving map displays that have a flight track depicted on them. Others are guided by what's called the ATM instrument, where it actually puts out a signal that we feed into the aircraft navigation system, where it guides the airplane laterally.
So the ATM stands for Airborne Topographic Mapper. We designed a supplemental system to the ATM. Some people call it the ATM Navigator. What it does is it couples into the aircraft's own autopilot and helps it to steer the aircraft as accurate as we need it to be. We can generally steer the airplane well within 100 feet and often within 20 feet of where we want it to be. And that means that if you imagine a line that represents our desired track, more than half the time that line will lie within the cabin of the aircraft.
Antarctica's harsh and often unpredictable weather determines when and where the Icebridge team will fly each day.
I've got rising terrain, 12 o'clock, 7 miles. Tally-ho. Tally-ho, and I'm going to start climbing here.
Pilots need perfect visibility of the terrain for safety.
We'll clear it. It does get steeper as we get closer to it, so we can pitch up a little bit.
Several science instruments need a clear line of sight between the aircraft and the ground to collect proper measurements.
Meteorology is obviously a very big deal with Icebridge. It essentially governs everything that we do on any given day. We have to fly down low and near the terrain in order for our instruments to work as they're optimally designed to work. So it means we need clear skies below the altitude at which we're operating in order to do this kind of work. We know from experience which parts of Antarctica are likely to have good weather and which parts are not. So we design the missions so that each of the missions has a maximum chance of success based on the likely weather scenarios.
We come up with about twice as many mission plans as we can possibly fly in the field, and that's simply so that we have enough target areas to choose from that have good weather while we are here in the field. And then we prioritize these plans.
We have to spend a very large amount of our time while we're in the field trying to sort of ascertain what the weather is going to do. It's a bit like reading tea leaves. It's a very inexact science. We depend entirely on what the meteorologists tell us through computer models. We talk a lot to the meteorologists here at the airport. They're terrific. They give us a lot of help.
The Chilean hosts provide everything from weather expertise to daily flight lunches for the Icebridge team. Airport firefighters and emergency responders are also prepared to help in case anything goes wrong with the aircraft.
So we don't use retread tires.
The DC-8 is not your typical airplane. Structural enhancements, new engines, and cutting-edge data systems make the aircraft a versatile, long-endurance platform for earth science research.
The DC-8 is uniquely capable for this kind of operation, mainly because of its long legs. It can fly for about 14 hours on a full fuel load.
We have to pretty much commute every day to Antarctica and commute back. And then we need also the capability of collect several hours of data. Typically on every flight we collect several terabytes of data all together. So we have 8 different science instruments on the aircraft. And in total it's a very complex set of measurements that we take over ice sheets, and doing it all at the same time in the same location from one airplane. It's really a tremendous resource.
It is amazing that a large airplane that was designed originally to be an airliner could be so diverse, but by its design it meets a lot of the requirements NASA had set for the type of science studies they wanted to execute using an airplane to support. This particular airplane was built in 1969, but many of the systems have been upgraded over the years to keep up with current technology. For instance, the airplane has a satellite communication system on it, which something like that didn't even exist when it was originally built. So what's nice about that is we can move data real time during the flights off the airplane to people anywhere in the world via the satellite system and then the internet, and they can send us information real time as well. We can X-chat, it's like texting back and forth to each other. We can send photographs, we can send technical data. You don't have to actually be on the flight to participate.
My view of this airplane is that it's the ideal airplane for the kind of mission we use it for, because it's built very strong. And in the old days when these were being designed and built, the airplanes were overbuilt to be on the safe side. We have a nickname for it. It's a DC-8, and the DC stands for Douglas Cable Car, because unlike the modern airplanes that use electronics and hydraulics to control the airplane in flight, this airplane is controlled with steel cables. So we do hurricane research, we fly through hurricanes, and we do a lot of different types of scientific research, and the airplane can take a lot of damage that would cripple other more modern airplanes, and this airplane still flies fine. It's like an old truck. It's solid and almost indestructible.
A wall of stickers at the mission director's console tells the story of the many missions the DC-8 has flown since it went into NASA's service in 1987. This aircraft and many others operated by the NASA Airborne Science Program fly thousands of hours every year all over the world to support a variety of Earth science research missions. It takes careful coordination and detailed planning behind the scenes to make these missions possible and to gain a better understanding of how our planet is changing.
I've always thought, like, oh my gosh, when you go to space, like, you don't have to grocery shop for like 6 months.
I think it's gonna actually put me on a schedule for eating. I am horrible at eating at all hours of the night. I miss lunch.
We're also talking about like beverages. Like, we can probably only drink powdered beverages or water. So nothing, no sodas.
No sodas.
Nothing carbonated. Yeah, it's just.
I think it'll be a little bit more healthy than what I normally eat. Plus, I get to eat everything with tortillas, and I'm from San Antonio, so. I will say we are doing this over a holiday weekend. You have huge barbecues and lots of great food, so I think I'm gonna want to eat some really good ribs and, you know,
and like
fajitas.
snacks.
Solemnly swear to eat all of the astronaut food and not cheat.
Never.
Never.
We're in this together, so if we feel
Never,
weak,
ever, ever.
we'll text each other. Maybe.
We chose 7 days out of the standard menu. You're going to have a protein, some carb, some fruit. The other large category of products that we have are thermostabilized products.
Which is sort of like a military ration that we don't have to refrigerate to keep fresh.
Can't do them in a microwave.
I was going to say, it looks like something that can't go in a microwave. I was going to ask because I didn't want to find that out the hard way.
We also have rehydratable food, which is this type in a vacuum pack where we have to add water, either hot or cold.
We're going to give you a syringe.
Oh, I don't like needles.
And it comes with a needle. So this is how you would rehydrate. Okay.
I don't think we would want to have that laying around our office.
Can I take that through airport security?
Yeah. It is the day before we start the food challenge, and I just went to go pick up all the materials from our wonderful food lab. So they're all packaged and in my trunk. I asked them what I should eat as my last real meal, and they said something fresh, maybe a salad. The problem is I was thinking nachos, so...
As I suspected, I wouldn't have time to eat in the airport. I'm probably going to grab something to eat on the fly. Hopefully there's some tacos.
So like I said, I was debating healthy or, not healthy. Of course, I chose nachos.
I did end up picking up some tacos, some shrimp tacos actually, with some rice and some beans. I told you I love tacos.
I think it's important to always choose nachos, so I'm gonna call this hashtag she chose nachos.
She chose nachos, he chose tacos.
So I have beef and mushrooms, rice pilaf, tomato and artichokes, and a wheat flatbread.
Well, I don't know about that. I have grilled chicken, mac and cheese, vegetarian chili. We're in Texas, come on. Cran-apple dessert.
Oh man, remember she told us to tear it so there's no extra pieces of trash.
Oh, so like if we were in space, this would all be floating around.
Yeah.
Once we open those packages, the food is what we consider to be liberated, and it can just float anywhere. And sometimes you find yourself using your spoon or your mouth to chase around the food and make sure you get it all in your mouth instead of stuck against the wall or somebody's face.
Let's heat up a bowl of water and set these green ones in there.
Idea.
Yeah. And it looks like it's getting to be the right consistency.
Yeah.
We might have not done hot enough water too. That might be why it's not absorbing like all the way.
Okay,
Well, this is good.
This is interesting. It's not bad. Wait a minute, what was this?
This is
Is good.
Yeah, the artichokes and tomatoes are good too.
Should I try and eat it like this?
Yeah.
Ooh. You should have just got straws. I could have been like,
Right? This is making my day. Like, this is a treat.
I have cran-apple dessert.
This would remind me of home.
Yum.
So it's been a long day, but I did not get hungry at all. I had my butterscotch pudding as part one of my snack. I was wondering if the workouts would be hard. They're pretty much the same. I feel really high energy, and I didn't even have coffee this morning. I'm actually really excited about this chicken, corn, and bean. This potato medley actually looks like some potatoes with spices and melted cheese on it. I'm very excited to get some melted cheese texture up in here. Little butter cookies look really delicious and super bougie.
So you'll see I have some Caribbean chicken, pesto pasta with some corn, tortillas, vanilla pudding, and some pears. I got a little bit better at actually making the space food today, but I punctured the actual corn. I cut through it, so I had to rehydrate it through the side. So lesson learned, this smells absolutely delicious.
It's my boyfriend's last day at his old job, so one of his favorite clients brought him these delicious, huge-looking cupcakes, so none for me.
Woo! Do you see that? This is science, y'all.
Be a nurse now.
I get. My mom would be proud. Like, Mom, I'm doing nurse things today. Look at this. Oh, okay. This looks like oatmeal. Do PR for NASA, they said. It'd be fun. What are you having for lunch? What's your main?
I have citrus salad, and then my main thing is fiesta chicken.
Ooh, I love fiesta.
Yeah, and rice. yeah, rice with butter.
And
so
tacos.
I'm really excited because I think our food's going to be warmer today.
I agree.
I think we did this right with some practice yesterday.
This is some smoked turkey.
Oh, God.
It's leaking.
Like
it smells funky. Cornbread dressing. And then some cauliflower. I'm not a fan of this.
Today we're eating in the LBJ room. So President LBJ is who Johnson Space Center is named after.
We should do a toast.
Oh, we should. Go LBJ. Woo! Oh, mine's closed.
And so here we go. This is really good. This is the chicken noodles. Let's try some of this green bean. Oh, that could use some hot sauce. The lentil soup. Ooh, it's hot. Ooh, hot. See, these are actually my tortillas. Astronauts on board the International Space Station can actually eat tortillas, and it's one of the things that they like to do because you can pretty much grab anything that's floating in space with them.
2 quick miscellaneous notes. I've been living a really scheduled life and waking up early and going to bed early because I've been having to wake up with enough time to make breakfast, and then I go to bed shortly after dinner just so I don't get hungry again.
I think Dan has a burrito.
Oh,
I am jealous right now. I went for pea. And queso.
Apples, fresh fruit.
Which may or may not be organic.
My snack was chicken in a pouch, so.
Mine was tuna in a pouch.
There you go.
Lemon curd cake. Looks kind of like your rice.
Not your grandma's lemon. I was just at the mall, and whew, that was a week time because all of my friends got some really good appetizers, and when you're just all sitting around the table together, I had to really stop myself a couple times to not mindlessly reach for some of their chips or pretzels.
What are you eating?
A cupcake.
And what is Isidro eating? Space chocolate.
Space chocolate.
Yeah.
How do you feel about the astronaut candy? Is it yummy?
Can you tell which one's the space food and which one is our regular Easter meal here?
Hey guys, what are y'all making?
Astronaut burgers.
My family gets to eat this delicious grilled food, and I get to eat a kind of brisket. It's space brisket and baked barbecue beans, so we'll see how that ends up being.
See this? Oh, it's coming apart.
Oh no!
Oh, save the meat.
It's Monday, so we're done at Wednesday morning. We're really ready to be done. The weekend was hard.
I was not able to eat any of the food that was at the festival. There were some jalapeno corn dogs, and I'm like,
sounds so good.
What is life right now? I can't even.
And we have curry chicken, green beans and potatoes. The potatoes have been iffy, but these look better than some of the ones. Cream of mushroom soup.
Oh. A little bit of India, a little bit of Texas with this countryness. So ready for this to be over.
Yeah, we're ready.
I need my social life back.
Yeah, no, I'm just.
I'm having milk today. Powdered milk. Ah!
We're nervous about the guests or the milk?
I'm more nervous about the milk, I'm not gonna lie. But something that I noticed while we've been eating this food is you have to have it really hot.
On the space station, we put it in a kind of a, it's almost like an easy bake oven.
Okay.
Where you just, and that does make a really big difference. So I gotta admit, when I was making lunch this morning, I wasn't thinking this was gonna be on camera. Leftover rice, some turkey.
But it's home cooked.
It's definitely home cooked. Yeah, I was a big fan of the garlic paste.
Garlic paste.
That can fix anything.
Okay, question, can you chew gum in space?
Yes.
Okay, because garlic, bad breath.
I wasn't trying to impress any of my crew members. We would use what we call food glue. Something, just make up something. Spray some olive oil in there, try to get everything to stick together a little bit, or like I said, the garlic paste worked well for me. When you get a few people with rice in their eye, then after that, you figure something out. It's a lot easier in space because we don't have to load the syringe. Like if you were trying to measure out 250 milliliters of water or 100 milliliters of water, we literally just dial that number and then press the button for hot or cold water.
So talk to me about tacos in space. Tortillas, are they great to have up there? Yeah. Oh, sorry. It just floated on his plate.
Gosh, if we had salsa, we did have salsa sometimes. You could put that on there. The salsa will stick to the bread. You can use the salsa for other things to stick to the salsa.
I'm from San Antonio, and I love tacos. So I told everyone I would make a space taco. Yeah. So it's a little bit leaky, extra moist.
It happens in space. Yeah. It doesn't rip off the edges, it just makes a bubble.
Gotta do the taco tilt because everybody knows. Good stuff. That's awesome. This was the Mexican scrambled eggs food lab.
They know what they're doing. We have some scientists back there. So is there anything that you...
Ooh, we did it! Way better than the LBJ toast.
Yeah.
Favorite meal? I actually really liked a lot of the breakfast food. And the shrimp cocktail was in fact very good.
Ooh, shrimp cocktail, but the scrambled eggs in a taco. Ugh, man, sorry. Done.
Se você quer vender online, seu negócio precisa se destacar. Vá para o Wix e-commerce e crie uma loja virtual profissional que atrai a atenção dos seus compradores.
We could do that.
If I were an astronaut.
So I was debating, this is the same debate I started with, nachos
Crie uma
or
vitrine online de
salad.
última geração e personalize como quiser. Exiba seus produtos em páginas incríveis.
But I can tell you, I really want some coffee.
Yes.
Some nice
regular coffee.
Hot coffee,
Like
not
a latte.
powdered. I gotta get some coffee.
And a soda.
Yeah.
This is not easy, y'all. I'm telling you.
We are going to the moon to stay, and this is how.
Hey, you're watching NASA TV, on the air and online every day, on this planet and beyond.
Alright, good morning everybody. Roll call, got the pilot, got the co-pilot, GEOC operator, mission director. Alright, flight mission crew, FCIFs are complete and flight currencies are all checked. Crew schedule has been published. We're NASA 872. Engine start expecting 0600. Estimated landing of 07 tomorrow morning. Subdivision durations approximately 24.
Alright, thanks everybody.
Como a maioria de vocês já deve saber, a definição de esquerda e direita surge no momento da Revolução Francesa, começando em 1789 na Assembleia dos Estados Gerais.
Powerful birds, capable of flying thousands of miles. Some species undertake long migrational journeys, a testimony to their strength and strength. Our bird will fly over 10,000 nautical miles, and will reach an altitude of 65,000 feet.
And decide where to send the aircraft.
Durante este debate na Assembleia, uma parte dos deputados ficou do lado direito da Assembleia. E esta parte dos deputados queria que o rei tivesse mais poderes, que as transformações fossem mais lentas, que não houvesse ruptura com a ordem tradicional. E à esquerda ficaram aqueles deputados que queriam limitar muito mais o poder real, ou até havia os radicais que queriam uma abolição da monarquia.
Esses dois modelos de pensamento político, a ideia de que nós devemos radicalizar e começar do zero e podemos montar a política do jeito que nós queremos, versus uma concepção de política que é prudente, que procura respeitar o conhecimento herdado do passado e manter o tecido social unificado, de alguma maneira estão presentes em todos os conceitos de esquerda e direita das democracias modernas, seja nos Estados Unidos ou na Alemanha, na Inglaterra ou no Brasil.
Ocorre que a direita compreende que a desigualdade é algo não apenas natural, mas algo que não tem solução. Logo, ao invés de tentar forçar uma igualdade que não poderia ser atingida, e aqui eu falo tanto de igualdade de oportunidades quanto da igualdade absoluta, seria melhor para a sociedade aceitar a desigualdade e tentar buscar uma sociedade mais eficiente.
Enquanto a direita luta para assegurar a ordem, a esquerda é aquela que, pautando-se no ideal de justiça, estaria disposta a arriscar a manutenção da ordem.
Para a esquerda, a liberdade de escolha pressupõe que todos tenham as mesmas oportunidades ou o máximo de igualdade possível no ponto de largada.
A direita luta para manter a tradição, enquanto a esquerda luta para romper com os privilégios de classe e de raça.
Ou seja, na economia, o objetivo da direita é a eficiência e os melhores resultados possíveis, entendendo que a desigualdade é natural e que, se for para tentar corrigir as distorções sociais, que isso não seja feito pelo Estado. Na economia, o objetivo da esquerda é corrigir as distorções sociais e buscar o máximo possível de igualdade, seja na vida das pessoas, seja nas oportunidades de elas subirem na vida e exercer suas potencialidades. O que eu falei até agora coloca a questão da direita e da esquerda em um panorama horizontal. No entanto, a coisa fica mais complexa quando separamos as questões econômicas das sociais.
Os liberais americanos, na verdade, eles são o pessoal mais voltado para a esquerda, eles não são tão conservadores.
Não, você não está confundindo, não. Os liberais americanos realmente não são conservadores, eles são liberais. Você que é conservador. Eles inventaram o liberalismo, cara. Junto com os ingleses. O termo é deles. Você quer saber mais? Parece um turista que pede sushi no Japão e reclama que não tem crentice. Os filósofos como Adam Smith e John Locke estavam querendo desconcentrar o poder e garantir liberdade. Eles achavam que não fazia sentido nenhum que reis e rainhas mandassem na porra toda sozinhos. Era um pessoal bem radical e progressista na época deles. Não exatamente conservadores, mas o contrário disso. Os pilares liberais que eles estabeleceram são simples. Tá? E a The Economist, a publicação liberal mais reconhecida no mundo, ajuda a gente a entender.
Liberalism is a worldview based on liberty and equality of opportunity. Liberals value free trade, open competition, and freedom of expression.
Liberdade e igualdade de oportunidade.
The idea that Adam Smith is most famous for is the idea of the invisible hand of the market. If government had a role in the market, it was simply to guarantee the enforcement of economic contracts.
O candidato óbvio que é aquele que une o liberalismo econômico a práticas conservadoras no campo do comportamento.
É um gigantesco vácuo. Perceba que ele não diz que o candidato vai preencher um gigantesco vácuo, ele diz que o candidato é o vácuo. Olha que agora que eu percebi isso vendo o vídeo, que lapso perfeito, que ele se definiu como um vácuo.
Aquilo que eu diria é que o conservadorismo, ou uma atitude conservadora, antes de ser uma expressão política, começa por ser uma atitude filosófica. E é a partir de uma posição filosófica que nós podemos chegar ao conservadorismo como política. Dito de outra forma, uma pessoa que se acha conservadora ou acredita que tem uma posição conservadora do ponto de vista político, sem ter uma dimensão filosófica do que é o conservadorismo, pode chegar a situações caricaturais de se achar conservadora, simplesmente porque é importante preservar a ordem, a segurança, sabe? No fundo é a velha política da cartilha.
Ser um candidato político liberal ou conservador?
Eu sou um candidato liberal na economia e me considero conservador nos costumes.
Liberal na economia e conservador nos costumes é tipo, o Estado não tem que se meter no mercado, mas tem que se meter no... Não dá para ser metade liberal e metade conservador. Ou melhor, até dá se você, além de candidato, for bilionário dono da Riachuelo, que recebe empréstimo a juros bem baixinhos do BNDES e é acusado de exploração de trabalho escravo. grande parte do liberalismo made in Brazil. Eles pegam um movimento super tradicional, tiram dele tudo que tem interessante. É tipo o que fazem com os samurais. Vamos aprender a lutar? Não. Vamos usar espada? Não. Vamos se matar pelo nosso país? Não. Vamos pegar só o coque.
Ou seja, há um confronto entre posturas libertárias e posturas conservadoras em qualquer sociedade.
Eu sou coxinha assumida, de direita, liberal.
Então é necessário inserir a tradição liberal em sua história concreta e perceber que, ao mesmo tempo que o liberalismo foi um avanço civilizatório frente às monarquias absolutistas da Europa, frente à ideologia e o modo de vida feudal, esses avanços civilizatórios sempre foram restritos aos proprietários dos meios de produção, homens brancos ocidentais, e que essa esfera de defesa da liberdade do indivíduo contra o autoritarismo, via de regra, excluiu e exclui a classe trabalhadora, as mulheres, os povos colonizados da periferia do sistema capitalista e também os povos racializados. Né?
Eu acho que é muito mais racional do ponto de vista político você defender a liberdade, a igualdade, a justiça, a ordem, o que quer que seja, partindo de Manaus das circunstâncias e da realidade. Podem existir situações, sobretudo em sociedades, por exemplo, onde existem diferenças de riqueza acentuadas que podem ser combustível para situações potencialmente revolucionárias. Pode haver situações em que a igualdade é o valor mais importante. E podem existir situações em que a liberdade é o valor mais importante. Em que uma sociedade encontra-se de tal forma estatizada que aquilo que é recomendável é que essa sociedade se liberalize e que promova certas liberdades.
O fato é que hoje no Brasil a gente vive a realidade que os liberais de verdade combatiam. Concentração econômica e de poder, privilégios hereditários e dinastias familiares. Nenhum desses liberais falsos realmente se dedica a desconcentrar poder e riqueza e promover a liberdade. Pior, muitos deles chamam de comunistas as pessoas que defendem postos de liderança para garantir a igualdade de oportunidade. Querem mandar para Cuba quem quer mais direitos para mais ser dono do próprio corpo, inclusive do próprio útero.
But I am. Couldn't get any of them. Couldn't get a single one of them to come back.
E o adversário do conservadorismo, na minha concepção, seriam aqueles que propõem uma mudança absoluta na sociedade, seja apontando para o futuro, que no momento que nunca existiu, a revolução, os revolucionários, ou um passado sempre idealizado, que seriam os reacionários. É isso, o adversário do conservador, então, é aquele que propõe uma mudança absoluta da sociedade, um reacionário ou revolucionário?
Eu diria que o primeiro adversário de um conservador tende a ser todo o tipo de pensamento radical. E o pensamento radical define-se pela ambição de pretender transformar radicalmente o presente rumo ao futuro, como acontece com os revolucionários, ou rumo ao passado, como acontece com os reacionários, que não são mais do que revolucionários do avesso. Ou seja, a escravatura era uma tradição. No limite, podemos até dizer que a escravatura era uma tradição útil, desde logo para uma sociedade escravocrata, mas não era uma tradição. Ou seja, não era uma tradição que respeitava a dignidade da natureza. Nesse sentido, não há nenhum motivo para conservar essa e, portanto, a posição conservadora tenderá a olhar para as tradições que merecem ser preservadas, mas, por outro lado, a reformar aquilo que não funciona. Porque a única forma de se garantir a sobrevivência de uma sociedade passa precisamente por atividades de reforma quando essa sociedade precisa de ser reformada. E, de certa forma, fantasiar é uma das atividades mais belas e profundas que os seres humanos podem entregar. Isso funciona na literatura, na arte, na música, na filosofia, até não funciona em política.
E aí descobriu com qual dessas linhas ideológicas você tem mais afinidade? Ou acabei levantando mais dúvidas do que já tinha? Deixa aqui nos comentários suas observações. Não se esqueça de deixar um like se concorda que esse é um conteúdo útil. Isso vai sinalizar para o YouTube que o conteúdo é relevante e ele vai mostrar para outras pessoas. Sugiro ainda inscrever e ativar as notificações para ficar por dentro de novos conteúdos. Quer contribuir com o nosso trabalho? Seja membro colaborador ou faça uma doação de qualquer valor para o Pix fixado no primeiro comentário.
Water is important for all life. We wouldn't have life on this planet if there wasn't water. When astronomers try to think about other planets and whether they have life on it, the first question to ask is there liquid water?
We have liquid water covering nearly the entire planet, 70% of the planet covered by water. There's water in our atmosphere, in the air, all around us. You don't find any place, any chunk of air in the atmosphere that doesn't have some water molecules or some ice particles or some water droplets in it.
Without water as part of the climate system, we would have wild temperature swings in our atmosphere that would probably make any planet uninhabitable. So water is a key driver.
So water is everywhere. Now, the way water begins, of course, it's a liquid out here, and the sun beats down on the surface and it warms the water, it evaporates it. Just like on your stove, you put your pot of water and your heating element below it heats it up and it boils off, you get steam or you get water vapor. Same way that the sun's energy will warm and evaporate water. That water rises in our atmosphere, and as it rises, temperatures are cooler aloft, and so you form clouds. Clouds are water particles. They're little liquid water particles. Some are very tiny, and they float around as clouds. They can also freeze and form ice particles, and those ice particles float around. Those are also clouds. As the atmosphere moves that water vapor around and those cloud droplets, they fall out of the sky and they come down on the surface and they feed our lakes and our streams. They make the soil wet so that crops can grow. Water is really a fundamental part of our planet. It goes back to the oceans and then it goes through this cycle again. So you get this constant heating up of liquid water, becomes a gas. It precipitates out onto the land, and it drives this, what we call the hydrological cycle.
So as water comes into the atmosphere, it has a number of effects. So it helps to make clouds, it helps to make rain, but water is actually a very important greenhouse gas.
Also, water carries energy with it. It takes a lot of energy to evaporate water. And then when water forms cloud droplets, it releases energy. So water is a big component of not only the hydrological cycle, the movement of water, but the energy cycle of the planet also, because it's a greenhouse gas and because when you evaporate water, it carries a lot of energy.
So the way it works is when we change the atmosphere, put more carbon dioxide in it, it gets warmer, and that allows the atmosphere to hold more water. The water is also a greenhouse gas, so that increases the temperature further, so it's a feedback effect.
Water, being a strong greenhouse gas, will actually amplify the greenhouse gas effect from these other longer-lived species like carbon dioxide and methane. So that's a very strong positive feedback loop which would keep driving the temperature up.
Or you could create more clouds and reflect more energy back to space, which is what we call a negative feedback.
So we have this complicated interaction between the positive feedbacks from the water vapor itself versus the clouds that it forms, giving you a negative feedback. And finding that right balance, that's part of what we're trying to understand with the entire hydrological cycle in the tropical part of the atmosphere.
And it turns out about half of the change in temperature of the atmosphere right now and the change predicted in the future associated with the increasing carbon dioxide is caused by this water vapor feedback.
Water comes and goes, and that's driven purely by the physics of how water works. It's a reactionary greenhouse gas as opposed to a longer-lived stable greenhouse gas. But water's the big player in the entire feedback loops of how the atmosphere works.
So it's very warm here in the tropics, and it's very moist. And so the air down near the surface has a lot of energy in it.
So deep convection in the form of thunderstorms and typhoons actually are more energetic. They go to higher altitudes.
And so it can go quite high. We see these big thunderstorms that develop, and that's this air being funneled up, just like a boiling pot of water. The air gets funneled up into the upper troposphere here and actually go very high.
And so that extends the troposphere upward to higher altitudes, and the temperature keeps decreasing as you go up, and so it's colder.
And so eventually, most of the water gets frozen out as you get up to these altitudes of 50, 60,000 feet. So it's incredibly dry, even though down at the surface in the tropics, it's very wet and moist. It's very high humidity, it's damp. When you get to 55,000 feet, about 16 kilometers up, it's incredibly dry.
You still get some water making it up to the tropical tropopause, and there the atmospheric motions transport air into the stratosphere. So air is transported into the stratosphere with a small amount of water that's left behind, and that's controlled by the temperatures at the tropical tropopause. So if the tropopause is colder, less water will make it into the stratosphere. If it's somewhat warmer, more water will make it into the stratosphere.
Above us, up at 40, 50,000 feet in the tropics, the atmosphere is going to warm up through this century. And because of that, there will be less freeze drying of this air going up. And so the thinking is that water might go up. Now, water is a powerful greenhouse gas, so if water increases at those higher altitudes, it will act to trap more energy at the surface. So it could cause the temperature to actually go up higher.
Climate change will have huge impacts on food supply, on ocean levels and flooding of coastal regions.
It's important to understand, put all of this together, to understand how water will change through the next century.
The more we understand the processes, the better off society will be because of it.
ATREX, when studying the tropical tropopause, is addressing a key uncertainty in our ability to predict future changes in climate in response to human influences.
It is believed that Guam was first discovered by seafaring people who migrated from Southeast Asia around 2000 BC. When Portuguese explorer Ferdinand Magellan arrived at the island in the 16th century, he found a highly stratified society, experts in the art of sailing and skilled craftspeople, the Chamorro. Since then, numerous expeditions have investigated this region of the Pacific, yet there are still many discoveries to be made and places to be explored. Although this time we'll be looking up, way up into the sky.
Attention on deck, engine start on my mark. That's number 7324. NASA 872. NASA 872.
My land-covered career really started in 2002 with biggest wildfire in Oregon's history, and that was the Biscuit wildfire. I, at the time, was doing botany surveys and looking for rare plants or rare mushrooms. And so I was spending a lot of time out on the forest looking at and taking photos and doing the documentation that a scientist or a land manager does. When that fire happened, it changed everything because we all had to react to this fire that was burning up some of the places that I'd literally been the day before. And it was mapping what was there and what was under threat, but it was also mapping the effects of the fire. We needed to find a way to look across 500,000 acres. And the only way that we could really do that was satellite data. If we can't get out and actually measure every single thing, what are we missing? And that's where citizen scientists can actually come in and really help traditional scientists to better understand what is happening around them, but also fill in these gaps.
The Global Learning and Observations to Benefit the Environment program is an international science and education program. It provides students and the public with the opportunity to participate in data collection and the scientific process. The Globe Observer app is one of these opportunities, allowing citizen scientists and students to take land cover observations around the world and submit them to a larger database. But what exactly is land cover? Dr. Eric Brown de Colston of NASA's Goddard Space Flight Center explains.
Land cover is really the basic form of the landscape that we have around us. So whether it's a forest or a desert, but it's really one of the components of the landscape that we can study from space.
Dr. Peter Nelson is a scientist who uses land cover imagery in his research.
I am a remote sensing scientist who studies land cover across the globe. I use satellite imagery to make maps of land cover and try to quantify what covers the Earth. Sometimes a satellite can't see what's happening underneath a tree canopy or what's happening underneath cloud cover. And so we really need people to go out there and to take these photos, to do these observations, to help fill in where a satellite can't actually make some observations.
Just like any digital photograph, land cover images are made up of a series of pixels to show what covers the Earth. A pixel, or picture elements, is the smallest unit of a digital image. When combined with thousands of other pixels, a picture is formed. Each pixel color shown represents a land cover type. It's from these pixels where ground verification or ground truthing come into play. You see, depending on what satellite is taking images, a pixel can cover roughly an area of 30 to 500 meters squared. For imagery captured by Landsat, a pixel is 30 meters squared, or about the size of a baseball diamond. However, part of that pixel showing forest might actually be water, or shrubs. By taking land cover observations, citizen scientists can help answer these questions when it comes to land cover maps. So, why are these land cover observations so important? Why are they taken in the first place?
We also are looking at how these components are changing over time. So deforestation in the Amazon or across the world, how are cities expanding? A lot of different things to study, and really the view from space is the way that we do it here at NASA. We have big supercomputers that simulate the physics of the atmosphere and the land, the interaction between the Earth systems. It's important to have that, that land cover map. It sets certain parameters. Those models can actually be used to look at current day conditions and weather. So based on these current conditions, what might the Earth look like 50 or 100 years from now? There's an element of understanding, but then also being able to predict into the future, what that might be like, what these changes may mean for us.
Each point shown here represents a real-world measurement of environmental conditions. Scientists use computer models to fill in information where measurements may not exist. By verifying the satellite imagery and using the data for these models, scientists can predict changes in our environment more accurately. One of these scientists using land cover maps to track urbanization as part of her work is Dr. Amita Mehta of NASA's Goddard Space Flight Center.
So urbanization changes terrain,
as well as characteristics of the surface itself. And so impervious surface is what we look at when we are monitoring flooding. When there are, say, parking lots or cement and concrete surfaces, they increase. So previously, if it was a farmland or something which was not built, and if that is built now, that water previously that could go or percolate in the soil and in the ground now cannot go in, and it stays there. Monitoring helps you to plan for it. So if you see land cover changing, even then you know that how water is going to flow in that region might change. If you have to send rescue out or you have to plan for relief activities, then if you know land cover, then you know where there might be help needed.
By using land cover maps and models that reflect changes over time, scientists can predict where flooding and other events may occur. With a changing climate, these predictions from models and land cover maps can help scientists better understand these changes and help communities prepare for them. But perhaps a more important reason as to why take land cover observations is you get to participate in a community of scientists, citizen scientists, and students.
So it's a very important component that the citizen science and students of the GLOBE program and GLOBE Observer can contribute to is by really giving us the information on the ground of what they're seeing around them and in front of them. And we hope over time as well how maybe some of these things are changing, because those would be very valuable for science.
I saw the value of having information before a hazard happens, because once that fire went through an area, we can never recreate that data. This is all important for us to share and put together because that's how we understand Earth as a system. All of these things end up affecting where we live, why we live where we do, and why we make some of the choices that we do.
To learn more about Globe Observer, check out the website at observer.globe.gov and download the app to start taking your own observations today.
Consider a busy street in a large urban city, what thoughts come to mind? Perhaps honking cabs, cars, or large crowds of people all trying to get to their destinations? Although that picture of a city may seem like a chaotic mess, the reality is that generally traffic and people move in a relatively orderly fashion. For the most part, cars stop at traffic lights, pedestrians cross when safe to do so, and everything works as it should, even if it's crowded. This system of traffic signals and rules of the road has been in place for many decades, so this type of movement is accepted as the norm for how we get around in a city. But what was city travel like before the invention of traffic signals? There are many stories of pedestrians dodging oncoming cars, horse-drawn carriages and fast-moving cars fighting for space, and just general mayhem ruling the day due to a lack of a well-thought-out plan. There were already rudimentary manually operated signals in operation, but with only a stop-and-go signal, they were not very effective. This left drivers little time to react when the command changed. It was clear when automobiles became more prevalent in the urban environment that a viable solution was needed to lessen the unpredictable nature of traveling in a city. That solution was found in November of 1923, when an inventor named Garrett Morgan came up with the answer. After witnessing an especially bad accident one day, Morgan designed and patented a 3-position traffic signal, which used an automated signal with an interim warning position, the predecessor of today's yellow caution light. With this invention, cities around the world began to adopt this new technology, making the streets safer for cars and pedestrians alike. That fundamental change for city driving came about 100 years ago. Ironically, today, there is a situation in our modern world that is in need of a similar solution, but it will take more than adding a yellow light to solve this new problem. NASA, the FAA, and more than 100 industry partners have tackled the proliferation of unmanned aircraft and the need to regulate and manage these small drones. Just in the past few years, more than an estimated 700,000 unmanned aircraft systems, or UAS, have been purchased and are flying around our skies. With the push for these unmanned aircraft to be used in our daily lives for tasks such as delivering goods to our doorsteps, monitoring traffic on highways, recreational uses, and for medical needs, to name just a few, imagine what our world would look like in a few years if a dependable system of control was not put into place. Many have questions how such a dramatic change to the airspace will affect our lives and safety, and with that, NASA has set out to create a research platform that will help manage large numbers of drones flying at low altitude along with other airspace users. Known as UAS Traffic Management, or UTM, the goal is to create a system that can integrate drones safely and efficiently into air traffic that are already flying in low-altitude airspace. With UTM, package delivery and recreational flights won't interfere with helicopters, airplanes, nearby airports, or even safety drones being flown by first responders. On this episode of NASA X, we will examine this award-winning UTM technology and see how it works, and better comprehend this innovative system. We will also take a look at the dedicated NASA team at various field centers and its government and industry partners to understand the work accomplished developing and testing new software in real-world research. And we will see the system in action and find out when these new innovations will come online. Not too many years after the first flight at Kitty Hawk, North Carolina, NASA's predecessor agency, NACA, began developing technology and systems that have revolutionized the way we fly. NASA took over this workload from NACA in 1958 and has continued to pave a path forward for the aeronautics community ever since. As the premier science and technology agency in the federal government, it makes sense that NASA was once again tasked with understanding and developing a new system to make sure the drone technology would be world-class and safe from day one.
Well, there's a lot of reasons NASA's doing this work, right? So we can have a nice working relationship with industry as well as with the government side, the FAA, the DoD, DHS, DOI, that whole alphabet soup of folks that are interested in this space as well. We can bridge that gap between industry, the public, and them, as well as bring our experience in the airspace and in aeronautics in general to solve the problem, right? So building that coalition, coming up with unique solutions, testing them in the field, making sure that we have all the parties involved. That's really the sweet spot where NASA sits for this kind of thing.
NASA teams have been looking at unmanned aircraft technologies for quite a while, trying to better understand how large, medium, and small drones will begin to be integrated into our national airspace. Early conversations with the Department of Defense just needed NASA to help transition unmanned aircraft into the U.S. airspace. But those needs began to transform to a bigger picture almost immediately.
When we got involved in this, it was a pretty simple problem that we were trying to solve. DoD was bringing unmanned aircraft back from theater. They needed to move them from one base to another. And so the question was, how do you get these very high-performance unmanned aircraft up into Class A airspace? So take off from restricted airspace and move through Class E airspace up into Class A. And that, that's real geeky sounding and all, but for the FAA people, this is really important. So that's what we thought the problem was. After we had started working in this just for a couple of years, along came this package delivery. So a whole new mission and a whole new set of actors came out. So it took on a whole new meaning. NASA then got very interested in how you manage the traffic as well as what the characteristics of the vehicle should be. So when we first started, it was all vehicle-centric. But then as we got real interested in UTM, or UAS traffic management, took on a new meaning of how do you manage all of these vehicles around, and it has just blossomed for that into hundreds or thousands of use cases, and everybody that could possibly think about delivering some service or some product to a household or between businesses now has an interest in the work that we've been doing.
With the knowledge of building a completely new system that would fundamentally change how vehicles move in our airspace, the team needed to carefully understand the major issues, so they took a step-by-step approach to make sure they were moving in the right direction. They first had to lay out the goals, which included, but were not limited to, allowing diverse, small UAS mix and airspace use. For example, package delivery, safely enabling scalability for the future, and establishing a highly efficient, predictable, safe, and affordable airspace operations system, all by developing and validating integration requirements and providing prototype software UTM systems for the FAA to further test.
So NASA developed this concept called Unmanned Aircraft System Traffic Management because we are expecting millions of drones and their operations in a day, which is magnitude order different than what happens with current aviation, where there are 50,000 aircraft, and at a time there are about 6,000 at peak in sky. So the question is, how do we manage these millions of drones without burdening the current air traffic control system? Now, there are fundamental differences in the way the manned aviation works and the drone operations will work. First of all, there is no pilot. Second, that these drones are small. Third, we can actually take advantage of digitization and connectivity across these drones by exchanging information to each other. So the idea of UTM is taking advantage of modern technology, making sure we don't overload the current air traffic control system. Now, one of the big parts of UTM is this managed by exception paradigm. In today's operations, air traffic controller is the only one that has all the information on the radar display. With UTM, we can connect all the information, and that information can be shared across all the operators in the sky. That allows us to basically say that just tell me what not to do, and I will figure out a path that will avoid other vehicles in the sky.
As PK mentioned, the system is a bit different than the air traffic control system used by the Federal Aviation Administration for today's commercial airplanes. UTM is based on digital sharing of each user's planned flight details. Each user will have the same situational awareness of airspace, unlike what happens in today's air traffic control.
Well, with the projected number of new drones coming in the commercial markets for a very large number of drones and operations, it's obvious that the current air traffic management paradigm, a human air traffic controller communicating with one or a handful of vehicles, will not scale up to the number of operations of commercial drones that people are thinking about. And so a new way of controlling this traffic had to be established or thought up. And so NASA came up with the idea and vetted it through the FAA and industry to have this automated system that really did not rely on human air traffic controller interaction. And a key to this is that industry would be providing these services. And this would foster competition and economic growth and such for the system. And so this whole development of this traffic management system, not manually controlled by the air traffic controllers, but by automated systems provided by third-party industry commercial providers really is a major change in the way air traffic management will be done in this country, and necessary to satisfy the vast number of new entrants in this growing drone market.
You think about the different ways that this system will impact people's lives. One simple one is ordering things online, right? In the future, you may be able to order something. It could be delivered to your house by drone in minutes to hours as opposed to days. That's one use case, right? So people can say, oh wow, that would be neat. Also, you can think about public safety, right? For example, fire departments. One thing they would like to do is to send a drone out before the truck can get there, right? It's possible for the drone to get to a site faster than a truck can, and they can survey the scene before their folks actually arrive. So again, that's a public safety feature that people can usually feel good that our system, a system like we've designed that may be implemented in the future, could help support. So let's imagine both of those things happening at the same time. Someone trying to deliver a hot dog to your house, and then actually a fire happening and the fire department wanting to get through. The system enables those kind of interactions, and it keeps the airspace safe, it keeps things from falling out of the sky, it keeps all the stuff working properly.
To begin problem solving, the team created 4 individual technical capability levels, or TCLs. TCLs are a risk-based development and test approach. TCL-1 served as the starting point of the platform, with drones flying simultaneously at 6 test sites, while each test site operated on their own schedule. TCL-1 focused on areas of remote population, low traffic density, rural applications, and work on notification-based operations. Researchers conducted field tests addressing how drones can be used in agriculture, firefighting, and infrastructure monitoring, and working to incorporate different technologies to help with flying the drones safely, such as scheduling and geofencing, which restricts the flight to an assigned area. After completing these valuable tests, the team then moved into the second stage of the testing, TCL-2. For TCL-2, NASA performed a 5-day flight test at the Nevada test site, with additional flights taking place for the national campaign at an additional 6 FAA UAS test sites. This testing was focused on monitoring drones that are flown in sparsely populated areas where an operator can't actually see the drones they're flying, known as beyond line of sight operations. Researchers tested technologies for on-the-fly flight adjustments in controlled airspace and technology to clear airspace for search and rescue missions or for loss of communications with a small aircraft. As the UTM team monitored these flights, researchers also introduced simulated aircraft into the same airspace occupied by the drones to add more complexity in the system. The drones flew profiles that simulated real-world uses, such as package deliveries, farmland surveys, infrastructure inspections, search and rescue missions, and video surveillance operations. This work was proven successful, and the team quickly moved on to the next phase, TCL-3. TCL-3 was flown at the 6 FAA-designated test sites and focused on creating and testing technologies that will help keep drones safely distanced and flying in their designated volumes.
The UTM project also included the development of onboard technologies to help mitigate the risk from drones, both for those in the air and on the ground. These technologies are designed to help recognize and address potential problems while in flight and without human intervention. One of these technologies allows a drone equipped with special sensors and software to autonomously sense and avoid other aircraft.
This capability level also tested vehicle-to-vehicle communications in areas with moderate UAS traffic density. Testing also included UAS ground control interfacing to locally manage operations, communication, navigation, surveillance, human factors, data exchange, and network solutions. Drones were also flown beyond visual line of sight and in close proximity in altitude and distance. The focused technology flight tests were conducted at Langley and Ames research centers and complemented the flight testing conducted at the designated FAA test sites. Both provided valuable information of the flight performance of the drones necessary to work within the UTM system. Since UTM is a new way to manage air traffic, human factor data collection in real-world conditions is critical to understanding the human-system interactions.
we're really breaking new ground on the way human operators interact with complex systems. And so being here helps us get data on exactly their experience with this system. So for example, we are kind of monitoring the communication patterns that they use. So UTM as a system is exchanging lots and lots of data, and that data can be presented to those operators a variety of ways. And they also have other ways that are not UTM to communicate with each other. They can communicate with each other over their radios. They can communicate each other through like texting applications, right? So we're kind of measuring all of those communication patterns to see what things are they talking about through UTM means and what things are they talking about with outside of UTM means, to really give us a sense for how well UTM as the system is supporting operators in conducting their operations.
Finally, TCL4 demonstrated how the UTM system can integrate drones into urban areas. Corpus Christi, Texas and Reno, Nevada were chosen as the test sites, offering the right mix of challenges to prove that UTM could work anywhere. The cities have large populations, many obstacles to avoid, windy weather conditions, reduced lines of sight, and fewer safe landing locations. TCL4 addressed these challenges using UTM systems and technologies on board the drones and on the ground. These include incorporating more localized weather predictions into flight planning, using cell phone networks to enhance drone traffic communications, and relying on cameras, radar, and alternate ways of seeing during flight to ensure drones can maneuver around buildings and land safely, all while communicating with other drones and users of the UTM system.
Over the progression of this project, where we are now is the most complex piece of it, right? So now we are testing in urban environments, in higher density operations, looking at kind of contingency or off-nominal situations. So that list of three things, urban environments, higher densities, off-nominal situations, those are all extremely complicated things to tackle. And so for us to be here tackling those things is the only way we could learn some of the things that are associated with those things. That would be all very difficult to learn in a laboratory setting. There are so many things that are really an opportunity that come from the geographic locations in which we are testing that give us these types of this data, everything that we learn from being here.
Although all this research took place here in the US, this new structure will be the framework used around the world.
UTM idea, concept, architecture is out there, and it's been endorsed by ICAO, the International Civil Aviation Organization. And if you look in Europe and in Asia, countries that are starting up their version of UTM, they're starting with this architecture that NASA developed. And so it's really out there, and we're participating in international standards groups to really kind of consolidate what the concept is and harmonize internationally.
The influence of UTM on future projects, I think, was something we're pretty proud of, right? The concept and the way of managing the airspace is really new. And people are seeing application of that to, for example, UAM and air taxis, potentially for high-E operations over 60,000 feet, space traffic management. All of these things can leverage what we've learned in UTM because it's about providing services to classes of operations where services aren't provided now and probably won't be provided. Right? So finding a solution to that really has benefited future work as well at NASA.
It's clear to see that a tremendous amount of planning, research, flying, design, and hard work went into this project, and that the UTM framework is here to stay.
I think we're really getting into a whole new era of aviation, right? Where we got completely new operations that weren't there before. We are envisioning a few years from now, maybe 10 years from now, a world where we'll be traveling through cities in small electric aircraft, for example, and we'll have our drones delivering medicine or delivering food or things like that. All this is really only going to be able if we set like a foundation where we can use our great new automation capabilities, networking capabilities, really making use of digital ways to coordinate all these different operations and all this air traffic in a way that just wasn't possible before. But the only way that we can actually do this is by shifting the paradigm entirely from this very human-centered approach that we've been taking over so many years to safely manage all this traffic that was existing for these new operations, to take an approach that is a lot more built around safe frameworks in which the different technologies can interact with each other, and where they actually are going to be able to provide the first level of safety layers and the core components of organizing all this traffic.
UTM is enabling airspace operations and providing access to users that was never possible before. It's opened up skies in a way that we can now enable different types of operations in the airspace, and we have a way to manage the traffic because of UTM, which gives tremendous societal benefit of reaching places, cargo as well as people, that was not possible before.
Low-altitude airspace is leading a revolution in flight, and a multi-billion-dollar industry is emerging as a result. At no time in history has aviation been poised to enter the lives of so many people. From package delivery to first responders to safety inspections to video documentation, every person stands to benefit in ways we have only begun to imagine.
We're really at a once-in-a-lifetime opportunity to be part of aviation. We see new aircraft that like we've never seen before. We have new types of software systems, scalable and cloud-based. We have new companies that are entering the space that we haven't traditionally seen in aviation so far, and we have really great collaboration amongst industry to work together, as well as collaboration with the FAA and aviation authorities to go ahead and make that happen. And that really sets us up for the next 100 years of aviation in a way that we haven't seen before.
The research and development completed on the UTM project has come to a close, but that doesn't mean that the final chapter of this technology has been written. NASA and its partners are planning future research and testing to mature these systems to the point that one day soon, flying drones in our neighborhood will be as common as seeing yellow caution signals on traffic lights. With the success of NASA's UTM project, that day is much closer than you may think.
The Webb telescope is closer to starting its mission of science, an historic look at the center of our galaxy, and the Crew 3 astronauts reflect on their mission. A few of the stories to tell you about this week at NASA. Our James Webb Space Telescope is in the phase of its mission known as Science Instrument Commissioning. This involves about 2 months of extensive calibrations and the last group of required setup activities before the telescope begins science observations this summer. A recent test image Webb took of a region of the Large Magellanic Cloud was compared to an image our Spitzer Space Telescope previously captured of that same region. The comparison demonstrates the improved clarity with which Webb can see the infrared sky. This ability could yield more detailed views of the cosmos and unprecedented discoveries. For more information about the Webb mission, visit nasa.gov/Webb. According to the Event Horizon Telescope collaboration, this is the first image of the supermassive black hole known as Sagittarius A, located at the center of our Milky Way galaxy. The Event Horizon Telescope uses data from a worldwide network of telescopes. Observations from NASA's Chandra X-ray Observatory, NuSTAR, and Swift Observatory were used to help astronomers study Sagittarius A. The astronauts of NASA's SpaceX Crew 3 mission reflected on their recent stay aboard the International Space Station during a May 11th news conference. NASA's Kayla Barron, Rasha Shari, and Tom Marshburn, along with Matthias Maurer of the European Space Agency, spent 175 days aboard the station conducting microgravity science research and technology demonstrations.
It was just this awe-inspiring experience and incredible honor to represent the NASA team and family in that role, and also to have our relationships as a crew grow through that expeditionary living and really supporting each other so that we could get the most out of every single day in terms of accomplishing our mission.
Crew 3 splashed down May 6th off the coast of Florida in SpaceX's Crew Dragon Endurance spacecraft. Our InSight lander on Mars has detected the largest quake ever observed on another planet. The estimated magnitude 5 quake occurred earlier this month on May 4th. The largest Mars quake previously recorded by InSight was an estimated magnitude 4.2 detected August 25, 2021. A magnitude 5 quake is comparable to a medium-sized quake on Earth, but is close to the upper limit of what scientists hope to see on Mars during InSight's mission. For the first time ever, researchers have grown the hardy and well-studied plant Arabidopsis thaliana in nutrient-poor lunar regolith samples collected during several Apollo moon missions. The plant is a relative of mustard greens, broccoli, cauliflower, and Brussels sprouts. This NASA-funded study could help pave the way for future astronauts to someday grow more nutrient-rich plants on the moon and elsewhere in deep space. Data from NASA's ICON mission has helped researchers determine that effects from the volcanic eruption on the South Pacific island of Hungatonga Hungahiape in January 2022 actually reached beyond Earth into space. The data show that in the hours after the eruption, hurricane-speed winds and unusual electric currents formed in the ionosphere, Earth's electrified upper atmospheric layer at the edge of space. ICON launched in 2019 to identify how Earth's weather interacts with weather from space. That's what's up this week at NASA. For more on these and other stories, follow us on the web at nasa.gov/twan.
Welcome to NASA's Jet Propulsion Laboratory in Southern California. Today we are celebrating the 1-year anniversary of the Perseverance rover safely landing on the surface of Mars. Now we are in an area of the lab called the Mars Yard, which is a simulated Martian environment where tests are done. And we have a couple special guests joining us today. We have Swathi Mohan and Rachel Kroniak, who are part of the Perseverance mission. Now, Swathi, you might remember her as the commentator who announced that the rover safely touched down on the surface of Mars while being in mission control, and Rachel is currently working on the science operations side of things. Now, they will be answering any questions you might have. If you would like to ask a question, use the Ask NASA hashtag or leave your comments in the chat box. Now, to get started, I have a couple questions for you. Swathi, can you believe it's been a year?
I can't. It's gone by so fast. I can't believe it's been a year already since landing day.
And around this time last year, you were in mission control. What was that like?
You know, leading up to the landing that week before, we were all super stressed and worried, making sure everything was going right. There's so many different pieces to landing that have to go perfectly in order to reach the ground safely. You know, we had our share of heart-stopping moments during the entry, descent, and landing, but to be able to confirm that we were on the surface safely, to get that first image back from Mars was just an incredible relief and an amazing feeling for the whole team.
And you were on the engineering side of things. Now, Rachel, as part of the science operations team, what are you and the mission up to now?
Yeah, so like Raquel mentioned, I'm on the science operations team, so I get to help build the plans of activities that we send up to the rover every single day. And a year ago, we landed in a place called Jezero Crater, which is home to an ancient river delta, which we think is a really good place to look for signs of ancient life on Mars. Now, we ended up landing a couple of kilometers to the east of the delta, and so for the past year, we've been spending our time exploring the rocks that make up the crater floor. And once we wrap up our crater floor activities, we're going to be making a beeline to the delta, which is going to be the next location for our next science campaign.
And as you can hear, it's kind of busy here in the Mars Yard today. Can you explain why this area is important for rover operations?
Yeah, so the Mars Yard is a really special place for us to test and practice all sorts of things with our Earth-based version of Perseverance named Optimism before we do them for real on Mars. And if there's anything that we know for certain about Mars, is that Mars is oftentimes unpredictable. And so the Mars Yard is a really special asset for us to be able to troubleshoot when we encounter unexpected things on Mars.
And what is your favorite memory of the Perseverance mission so far?
Gosh, it's so hard to pick just one because it's been a really exciting year. A memory that sticks out for me was a couple of months after landing when we were getting ready to send up our first activity plan, telling Perseverance to collect our first rock sample. So this was something that we were working on for weeks and months leading up to that day. So when the day was finally here, it was super exciting. It was also very nerve-wracking, and like Swati said about landing, it was a huge relief once we were able to do it.
Sure. What about you, Swati?
I echo Rachel in that it's really hard to pick just one, but I would have to say it's pretty hard to beat landing day. It was the culmination of all of the work that we had done for so many years, you know, the hard nights and the long nights and the testing and the good things and the bad things kind of coming together with all the memories associated with it for that successful day that kind of encapsulates the whole mission for me.
And after that, what did you do next?
So Rachel mentioned the first sample acquisition on Mars. That's really important actually, because Perseverance was the first leg of Mars sample return. So the fact that we confirmed that we got one sample successfully kind of kicked off a multi-agency effort to bring those samples back to Earth. I'm working on one part of that campaign, which is a lander that will go to Mars with a rocket on it that is intended to get the samples off the surface of Mars into space.
Now, after you wrapped up the mission, is that typical for an employee of JPL to start on a new mission?
It is actually. When we wrap up one mission, we often go to the next one that needs the help. So the Mars 2020 Perseverance team actually went to multiple different missions. They went to Psyche, which is next up in launch this year, to Europa Clipper, which is next on about a few years from now, and then also to the Sample Retrieval Lander, which has a little bit longer runway until it launches.
As you can tell, it's really, really noisy here today, but we're going to see some familiar faces, as Swati mentioned, and we're going to get to some viewer questions now. So if you have a question you'd like to ask, please use the Ask NASA hashtag or leave your comments in the chat box. So first up, Provinx on Instagram asks, how long did it take to complete the rover's construction? Swati, do you want to take that one?
Sure. So Mars 2020 as a project started very soon after Curiosity landed, around 2011, 2012. That's when the design work started for the mission in general. The rover construction for the actual hardware that would be sent to Mars started a little bit later than that, around the 2018 timeframe, to get ready for a launch in 2020.
And I have another question for you. Shiva MSH24X on Instagram asks, what did you guys learn from Curiosity and how did it affect Perseverance's design?
We actually really appreciated the fact that we could analyze Curiosity's designs both in all phases of the mission, the cruise, the entry, descent, and landing, and the surface, and to make the changes to improve on it for the parts that we could. Now, we had to be very targeted about what those changes were, so we sought to improve in key targeted areas, and then we added to Curiosity design to allow Perseverance to enable its mission by adding the new sample capture system, adding better wheels in order to allow Perseverance to drive farther and faster, adding the whole terrain navigation system to allow Perseverance to land more accurately than Curiosity could.
And you can kind of see some of that in this Optimism rover behind you because it's a twin, correct?
This is a twin of Perseverance, correct.
Great. Now, Rachel, Jocelyn on Instagram asks, what is the most interesting discovery the rover has made so far?
Yeah, that's a great question. And so, like I said, we came to our landing site, Jezero Crater, to look at the ancient delta system that we have preserved there. Now, we've spent most of our time so far exploring the crater floor. And leading up to landing, we weren't really sure what we were going to see once we landed in the crater and explore the geology and the rocks that make up the crater floor. It was actually kind of interesting because our science team was sort of split 50-50 in groups that thought we would see sedimentary rocks on the crater floor, so things like lake deposits similar to what Curiosity has been seeing in Gale Crater, whereas the other half of the team kind of thought we might be seeing igneous rocks in the surface exposures on the crater floor. After a couple of months of exploration and a couple of samples that we've collected, we've actually confirmed that almost all of the rocks that we've been seeing in the crater floor are indeed igneous in origin, so that's been a surprise to us.
Thanks, Rachel. Now taking it back to entry, descent, and landing, Swati, Free Advice on Twitter asks, did you have any backup plans in case any failures happened, including the landing?
So when we design entry, descent, and landing, it's really hard to test that in Earth because you can't put it together all the way. So to make sure we have all our bases covered, we do try to build in as much protections as we can because the rover has to do it all on its own. There's no opportunity for us in mission control to be able to give the rover any instruction to change. So for example, one of the nice backup features that we had was that if we had any hiccups with the main computer that was controlling during entry, descent, and landing, we did actually have a mechanism that we had the backup computer on standby that if something happened, we could swap to the backup computer and continue entry, descent, and landing successfully.
Yeah, and speaking of all the cool parts, Rachel Nick on Instagram asks, what is the coolest piece of technology on the rover that helps scientists gather info?
Oh gosh, that's another tough one. It's hard to choose just one. I think, with all of the missions that we've been sending to Mars, it's really important to be able to interpret the geology of our landing site. And we do that mostly by taking pictures of our surroundings. So I would have to say, if I had to pick a piece of technology, it would probably be the cameras that we have on Perseverance. Perseverance has 23 cameras. Many of them are color cameras, some of them can even zoom, and so we can really image all of our surroundings in really incredible detail with Perseverance.
Thanks, Rachel. Lots of questions coming in. Swati, Juan Camilo on Instagram asks, what programming languages are involved in the rover's daily functions?
Yeah, that's a good question, actually. So the software on board the rover is primarily in C, but we use many different languages here on the ground to do different functions like analyzing data or running test scripts. So we've used things like Python and MATLAB and C here on the ground in a variety of different functions to help the rover do its operations.
And 24/7 Canes on YouTube asks, what have we learned about the weather on Mars and how would it affect future missions? I don't know which one of you would like to take that.
I can take that. So we have a couple of instruments on Mars that are on Perseverance that are helping us characterize the daily environment. We have an instrument called META, which is sort of like our weather station on Mars. And so we're looking at things like the weather, the radiation, the dynamic environment that's changing every day on Mars. And we found that there's quite an active atmospheric cycle on Mars with Perseverance so far.
Great. And Scout on YouTube, first off, gives you a shout out. Thank you for all the amazing work on the mission. Now, what is on the horizon for 2 years in terms of scientific goals, experiments with the rover, and possibly helicopter?
Yeah, so we have a couple of main mission objectives that we hope to accomplish with Perseverance. The first is to characterize the geology of our landing site, which we've been hard at work doing in the last year, looking at the crater floor. Looking forward, we're going to be exploring the delta in the next year of our mission, and then beyond. beyond the delta, looking at sort of the margin of the crater and hopefully beyond the crater itself in future years with the mission. We also plan to look for signs of ancient life in the rocks that we're exploring in Jezero crater, and so we have a really sophisticated set of scientific instruments to tell us about the mineralogy and texture of the rocks in a really fine scale detail. And so we're constantly learning more about the geology around us, and we're going to be exploring a whole bunch of really exciting places over the next couple of years.
And we have a question from Richard on YouTube who wants to know, does Ingenuity need to be in the line of sight to communicate with the rover? Like, how far away could it be to stay in contact?
I can take a stab at that one. Yeah, so
we can also get back to them too.
I can speak a little bit to the helicopter. So our sidekick helicopter Ingenuity was meant mostly to be a technology demonstration for to be able to demonstrate that we can achieve powered flight on another planet. And in sort of standard NASA fashion, we really exceeded our expectations with Ingenuity and transitioned more into an operations demonstration with the helicopter. And so Ingenuity has been really helpful in sort of scouting the places that we want to visit and places that we actually can't visit because of the terrain with Perseverance. And so we've been using Ingenuity so far in the last year beyond our technology demonstration to help us plan in operations.
And then Saeed91EK on Instagram asks, why doesn't the rover examine the samples that it collects?
Yeah, that's a good question, and it turns out that we actually do in a way. And so when we find a rock that we're interested in sampling, we drive up to it. But before we collect a rock core sample, we actually use one of our different coring bits called an abrasion bit. And what our abrasion bit allows us to do is drill the upper couple millimeters of the surface and reveal sort of a 5-centimeter abrasion patch that lets us use our scientific instruments that we can put in very close proximity to that fresh surface to tell us in really fine detail what minerals are there, elements are there, and what the texture looks like at a really fine scale. And so once we're done with the abrasion and the analysis of the abrasion patch, we can then choose our coring target. And we normally pick a coring target that's pretty close to the abrasion patch. And of course, once we collect our core sample, it gets sealed into one of these ultra clean sample tubes. This is a full-scale model of what the sample tubes look like. And once we collect the sample into the tube, of course, it gets sealed and stored for later retrieval to Earth, hopefully in the future. But once it's in the tube, we can't analyze it, like you mentioned in your question. And so by studying our abrasion patch with our science instruments, we use that data sort of as a proxy to help us understand what we could be expecting to find in our core samples.
And how many samples have you collected so far?
So far, we've collected 6 rock cores of the crater floor in our past year. We're hoping to collect about 2 more before we wrap up our activities on the crater floor.
Now, Twalo on YouTube asks, is the Mars rover behind us real, or is it a copy of it? It'll be nice to speak more of it. Swati, if you want to kind of touch on what parts were part of EDL, and then maybe entry, descent, and landing, I should say, and Rachel talk more about the science. Go ahead.
Sure. So Optimism is real. It's a fully functioning rover that we use here on Earth. So it does have a few modifications from the rover that is on Mars, primarily to allow it to work here on the Earth. So the wheels are a little bit different in terms of suspension to handle the Earth gravity. But in terms of the electronics on board, in terms of the cameras and the processing, we try to make it as similar to Perseverance as we can, so that when we are testing our sequences, our planning here on the ground, we can have a really good expectation of how it'll work once it's on Mars.
Yeah, and then from a science perspective, you can see mock-ups of all of the different instruments that we have on the rover on Mars for real. So we can see, looking at us here is one of our cameras on the end of the robotic arm. We also have the remote sensing mast, which at the moment is pointed away from us, but has a couple of additional cameras on top of it that serve as sort of our eyes as we're exploring the terrain around us.
Great, and then Oleski on YouTube asks, what was the biggest challenge during the mission that you had to overcome?
Oh, that's an interesting question. There was a lot of challenges during development, but from my perspective as the guidance navigation operations lead, I would have to say rethinking how we had to do operations and our final assembly in the light of the pandemic was one of the big challenges. You know, we've never had to fly a mission like that and it was constantly a tug of war between the personnel safety here on Earth and the safety of our hardware either in space or in the final assembly. So constantly having to make those trades as to how we were going to balance and how we would rethink what it meant to be working remotely with our spacecraft was a big challenge. And I'm really impressed with the team for pulling together and pulling through for an on-time launch in spite of the pandemic hitting just a few months before launch and making it all the way to Mars for a very successful landing. And the entire time we've spent since then working as the pandemic's been ongoing.
You made the whole thing look easy. Congratulations to the team on that. Rachel, what about for you?
Yeah, since we've been on the surface, we've encountered our fair share of curveballs from Mars too. I mentioned the first time that we sent our sampling plan up to the rover to collect a sample in one of our sample tubes. Once that plan executed on Mars, everything worked perfectly from our hardware perspective. But then when we started to analyze the data that came down, we actually saw that the tube was empty and didn't contain a rock sample as we were anticipating it would. And so we constantly have to adapt as Mars throws us curveballs and challenges, but everything from the rover's perspective has been working flawlessly.
Great. And for Swathi, Tyler Williamson on YouTube asks, actually for both of you, what type of degree do you need to become a NASA engineer?
That's a great question. There are so many different ways to contribute to NASA. You know, we generally like to look for some degrees in science and technology, and it doesn't have to be just one particular area of science or one particular area of engineering. You know, find what makes you the most interested, where your passion is, and there's so many different ways to apply that to NASA programs, whether it's, you know, geology of Mars or chemistry as we think of planetary protection, or, you know, even biology as humans go into spaceflight, or in the traditional like structures and controls and mechanisms. You know, we need all of those different fields in order to support NASA missions, in addition to all the non-technical fields like the writing and the publicity and things like that.
It's a wide range of jobs. What about for you, Rachel?
Yeah, I couldn't agree more. I think one of my favorite things about being a part of the Perseverance team is that no two team members have the same path or the same level of experience or background. And so you really have to find what interests you and pursue that and work really hard.
And Erica on Twitter asks, what do you hope to accomplish with this mission overall?
Oh yeah, so I can touch on that first. So we talked a little bit about sort of the mission objectives that we hope to accomplish with Perseverance.
It's a wide range of jobs. What about
for many
you,
reasons?
Rachel?
And for I couldn't agree more. I think one of my favorite things about being a part of the Perseverance team is that no sample tubes with us to Mars, and we hope team members have the same samples of Martian or the same level of experience or background back to analyze here on Earth. And so you really have to find what interests you and pursue that and work really hard.
We can actually unleash the whole arsenal
and Erica on Twitter asks, what do you hope to accomplish with this mission overall?
At them in the hopes of finding signs of
yeah, so I can touch on that first. So we talked a little bit about sort of the
life
on the mission
Mars,
objectives that we hope to accomplish with Perseverance.
It's a wide potentially change how we look